BGC working group. I'm Gretchen Keppel-Alex. I'm at the University of Michigan, and I'm one of the external co-chairs.
And I'm Abby Swan, and I'm at the University of Washington. I'm the other external co-chair. And Matt Long is over here, who's internal NCAR co-chair.
Yep. So yeah, we sort of broken this down to do like land BGC in the morning and ocean BGC in the afternoon. So we're excited to try to fully represent the coupled system by having land, ocean, and atmosphere represented in our talks.
We wanted to remind folks of the Code of Conduct from NCAR, which is posted up here on the slide. Make sure that we're hearing from all voices and being constructive in our feedback, et cetera.
Yep. And we have like some logistics or housekeeping to note about the room. One is speakers will have these microphones on. Put them in the middle of your body so that if you turn your head, you will still be picked up. When you take it off, turn it off so that we're not getting like static in the transition. Don't put your microphone in your pocket with your phone because that will also give static. And there's microphones on the ceilings, those two discs with the red. When those are green, those are live. So during Q&A, try to not ruffle papers or talk to your neighbors because those will pick up the noise and degrade the quality of the sound for the discussion for the folks who are participating online. We need to log in online so that we can monitor the chat. All right, the folks who are online, please use the chat. If anybody in the room wants to log in so you can participate in the chat, that would be great. We'd like to make it as fully interactive with the folks who are here locally and the folks who are remote as possible.
You can also raise your hand online if you want to ask a question live, and we will call on you so that you can do that over audio.
Yep.
And for people in the room, don't touch the screen.
Yeah. So I think those are sort of all the logistics. We're excited to be back in person, and
so we'll have 2 sessions on land biogeochemistry this morning, and then we'll break for lunch, and after lunch we'll do ocean BGC.
Yep. Cool. All right, and unless Matt, do you have anything to add? All right, so our first speaker is going to be Amy Liu.
Great. Can folks hear me?
Our first speaker is going to be Amy Liu from the University of Washington, talking about quantifying the influence of stomatal behavior on photosynthesis in the Amazon.
Cool. Thanks for the introduction, Abby. I've had the pleasure of having many collaborators, listed them up there, and the funding for this project is from DOE and NSF. Oops, sorry. There you go. So to start off, we all know that plants have stomata on leaves that regulate gas exchange with the atmosphere. So we have an open stomata with open stomal or high stomal conductance, and we have a closed stomata with low stomal conductance. And so why do we care about stomal conductance? Well, changes in stomal conductance drive changes in water flux, which can impact the water cycle and affect the water availability and the risk of extreme climate events like droughts, heat waves, and floods. And changes in stomal conductance can affect surface properties like evaporative resistance, and Marie Siligu et al. 2019 has showed that changes in evaporative resistance can then further affect surface temperatures. In CLM, stomal conductance is represented by the Medellin model, equation shown here, and we're interested in the Medellin slope, which is boxed in green over there. And this is a figure that I believe Katie showed yesterday from Medellin et al. 2011, and the Medellin slope is quite literally the slope of that fitted line against those data points. So this is a plot from Medellin et al. 2015 showing the estimated Medellin slope based on field observations. So on the y-axis here, we have the estimated Medellin slope, and on the x-axis, we have temperature. Each color represents a plant type, and as we can see here, there's a huge range of Medellin slope values across and within plant types. And this large range can lead to large variance for plant-related processes. So in CLM, 1 melon slope values is used to represent each plant type. So for example, this is the estimated melon slope values for the broadleaf evergreen tropical trees based on the Lin et al. 2015 data. And we have a low of 1.7 to a high of 9.11, but a default value of 4.45 is the one value used for CLM. And so this really begs the question, what would happen if we use a different melon slope value? So we're going to focus on the melon slope parameter, and water use efficiency is related to melon slopes proportionally, and is defined as photosynthesis over transpiration. And this is a simple visualization showing the relationship between water use efficiency and the melon slope parameter. So with the increase in melon slope, we would expect a decrease in water use efficiency. However, if we don't consider water stress, we see a different relationship between photosynthetic rate and the melon slope parameter. So with an increase of melon slope parameter, we would expect an increase in photosynthetic rate. So these two plots show what could happen if we change melon slope, but we don't know which one would hold true when we actually do change the melon slope parameter. So we're going to vary the melon slope and see what happens. So we're going to start with a default melon slope parameter, and based on the Lin et al. 2015 data, we're going to have a low and high melon slope as well based for each plant type. So I'm going to show the high melon slope case first. So this is a spatial plot of the differences in photosynthesis between the high and default melon slope, where brown corresponds to a decrease in photosynthesis and a green corresponds to an increase in photosynthesis. And we can see for the high melon slope case that there's only really brown in the plot, and so decreases in photosynthesis are pretty consistent globally. Ooh. Okay. And if we compare it against the unstressed photosynthetic rate plot, we would have, if this plot were to hold true, we would have expected an increase in photosynthesis, which we clearly don't see. So it's clear that the water use efficiency plot is a more dominant player here, or holds true more. But if we take a look at the low melon slope case, so that's the spatial plot on the left here, we see a lot of color, a lot of green, a lot of brown. And this really shows that the response to a low melon slope is regionally dependent. The response, yeah. And since it's pretty complex, we're going to focus regionally, break down regionally to understand what's happening for the low melon slope case. And we chose to focus on the Amazon first. So the red box is just to constrain the data we analyze. And photosynthesis increases in the Amazon with low melon slope. Our water use efficiency plot still holds true. We see an increase in water use efficiency with a low melon slope. And I'm going to walk through mechanistically why that might be the case. We see an increase in photosynthesis with an increase in water use efficiency. So we see an increase in both water use efficiency and photosynthesis. We saw decreases in transpiration, which is expected with an increase in water use efficiency. We also saw changes in heat flux, or a decrease in latent heat flux, and an increase in sensible heat flux, which is also as expected. But we actually also see a pretty large decrease in water stress and an increase in soil liquid content. So we think that the changes in water due to the low melon slope and an increase in water use efficiency caused an increase in photosynthesis. However, this was for the uncoupled case. If we turn on the atmosphere, so we couple the atmosphere, we actually see something different happens to photosynthesis. So on the left, we have a spatial plot of the Amazon of the coupled case with the difference in photosynthesis for the low minus default melon slope. And on the right, we have the same spatial plot we saw earlier for the uncoupled case. And if our increase in water use efficiency were to hold true, our decrease in photosynthesis that we see in the coupled case would be pretty confusing. So we're going to walk through the same mechanisms again to try and figure out why this might be the case. It turns out that the impacts on water are similar in both cases. There's similar decreases in water stress and increases in soil water content. And it actually also turns out that due to atmospheric feedbacks, we see a much more significant increase in temperature. And we think this is why we see a decrease in photosynthesis in the coupled case. So I've shown you two different configurations. so coupled and uncoupled with the low Mellon slope case. And these two configurations have given us totally opposite responses. But there's also multiple other factors that can affect small conductance that we're interested in exploring. So the first is land-atmosphere coupling that I showed previously. The next is we're interested in what happens when we increase the CO2, since that changes the relationship between carbon and water fluxes. And we're also interested in dynamic leaf area compared against a fixed leaf area, since leaf area would change the relationship between water sufficiency and the total fluxes of carbon and water. And on top of all of these factors, we're also going to continue to look at the low and high Mellon slope compared against the default Mellon slope cases. So this is a nice little table that shows all of the runs that we've done. And to put things in perspective, the two little boxes in red are the two configurations that I showed earlier that we've compared. So there's a lot more runs to analyze and compare, and analyze and compare. But I'm going to go back to the two configurations I showed earlier in the bar chart form now. So this is a bar chart showing the percentage differences of photosynthesis in the Amazon. So the y-axis is the percent difference in photosynthesis. And we have the coupled and uncoupled case that I showed earlier here. And we see that it's two completely opposite signs of response. So now I'm going to keep the uncoupled case and compare it against, which was a fixed leaf area, and compare it against the dynamic leaf area case. And we see an amplification of response, photosynthetic response. And now I'm going to take that same uncoupled fixed LAI case, which is actually 1 times pure industrial CO2, and compare it to doubling the CO2. And we see a dampening effect with the doubling of CO2. And this is a bar chart of the difference in photosynthesis of all of the runs in the Amazon. And we see that for the response to the change in Mellon slope is pretty different depending on the configuration. So there's a lot more to explore that we're going to work on explaining why we see the different responses we do. So to summarize, we first showed that there's a high Mellon slope results in low water use efficiency, which is consistent with global decreases in photosynthesis. Next, we saw that a low Mellon slope's effect on photosynthesis is pretty regionally dependent. And finally, we saw that the impacts of Mellon slope on photosynthesis, water flux, and climate is pretty complicated and varies across model configurations. Cool, thank you.
You can take questions in the room, and folks online are welcome to raise hands or type in the chat.
Okay, Sanjeev has a question in the chat.
Yeah, Sanjeev, go ahead. You can unmute yourself. We can't hear you yet, though.
In the coupled case, did the precipitation decrease in the coupled case? Or have you looked into the precipitation of the coupled run?
The precipitation of the coupled case.
Precipitation of the coupled case. Yeah. I don't have things.
So,
You say it a little louder. So
Yeah, precipitation did decrease for the coupled case.
okay, thank you.
Katie?
Great talk, Amy. This is really cool to see all the differences in this bar chart. I guess I'm wondering if you're thinking about how the different factors combine, if they're linear or not. Are there ways to kind of tease out when you have one thing changing versus multiple things changing?
That's a great question. And great suggestion too to look at next. We haven't teased it out yet, but if you have suggestions on how, all ears.
Yeah, great.
I see a hand online. Sing, do you want to go ahead? I'm sorry if I pronounced that incorrectly. The person who has their hand up online, you're welcome to unmute.
Jyoti, yeah.
Oh, Jyoti. Okay, sorry. Go ahead and unmute yourself. Maybe the hand is up in air. And you're clapping. Or clapping, yeah, we had some of that before. Any other questions here? Peter, go ahead.
I was just going back to Sanjeev's question. Do you think it's the coupling, or is it the fact that the climate is different that is the reason why you're seeing such a strong difference between your coupled? So if you were to take the output, let's say, of a coupled run and put that through uncoupled and put it in uncoupled, so you just did the atmospheric forcing, do you think you would see the same response? I'm trying to ask you, is the coupling or whether it's the climate difference? Do you think it's the...
I think it's the coupling since due to the atmospheric feedback. So I think if you took the same atmosphere and took it in an uncoupled case, maybe you see a similar response. Okay.
I think that's hard to separate out, but
Right.
yeah, 'cause
Yeah.
the atmosphere responds, and then you can get more surface temperature change locally. Joji, do you want to try again? Or type your question in the chat and I can read it. So the question is, having a spatial variable Medlin slope for each PFT might improve stomatoconductance. So instead of having one Medlin slope for each PFT, how would it be different if we had like a gridded map of stomatoconductance or Medlin slope?
I feel like it'd be hard to define the spatially.
Can you speak up, please? I can't hear you.
Oh, yeah, sorry. I think it'd be pretty hard to find like the.
So I think your mic is off,
Uh-huh.
or the speaker in here of your mic is off so that we don't get echo in the room. So you just have to project for those of us in the room.
Just talk louder.
Oh, talk louder? Okay. So I think it'd be pretty difficult to spatially assign Mellon slope values. And I actually, we vary the PFT.
Yeah, I guess the question would be, do we have enough information to even begin to do that? The question you could ask in an experiment, but I don't know if other folks have ideas about how well we would know what to assign. Okay, any further questions? All right, we can move on next to Pierre's talk. You want to help us? Well,
Yeah, turn it off.
so Pierre, are you there? It doesn't look like Pierre is online. So, Does anybody know his phone number? They could text him and we could loop him in later. Yeah, I searched for his name. Emma, would you be willing to do your presentation now?
Sure, I can go ahead.
Okay. So I think that you should be able to share your screen now.
Okay. All right. Can you see that?
Yes, we will have to get you full screen in here, but we can see your presentation fine and we can hear you.
Okay, cool. Should I go ahead?
Yes, go ahead.
All right, thank you. Hi, everyone. I'm Emma. I am a postdoc with the Insight Project, and I'm based out of the University of Montana, but have been working on a collaboration with Will Weider and some members of NCAR, looking at how Fourier stoichiometry is represented in the community land model, and how that representation influences projections of the land carbon sink. So in several of yesterday's talks, we saw that there's a lot of uncertainty in land carbon sink estimation. And a lot of that has to do with our understanding of how vegetation will respond to the carbon dioxide fertilization effect. So some of that response is likely governed by vegetation stoichiometry, which is the proportion of carbon to nutrient elements in plant tissues. So today I'm going to focus mostly on foliar carbon to nitrogen ratios. And as atmospheric CO2 rises, those carbon to nitrogen ratios increase as plants assimilate more carbon, but they might need to take up a matching amount of nitrogen and phosphorus to maintain some of these internal stoichiometric ratios as that carbon assimilation increases. And we're not certain about the degree of that flexibility of that stoichiometry, but there is some evidence in a lot of Earth's ecosystems that carbon to nitrogen ratios increase under elevated CO2. So this study is a meta-analysis of free air carbon enrichment study data. And they demonstrated that across plant tissues, as well as in soil pools, there is an increase in C to N under elevated CO2 relative to ambient CO2. And today I'm going to focus on these leaf foliar values. There's about 15 to 20% increase in foliar C to N under elevated CO2. And this is seen in these free air carbon enrichment studies. It's also seen in a number of natural systems and is a fairly common phenomenon across ecosystems as atmospheric CO2 rises. And this then is likely to influence how productive these ecosystems can be in the future because of those internal stoichiometric balances. However, we don't currently have a representation of C to N, foliar C to N in models that changes in response to elevated CO2 so that it increases progressively over time, as is seen in some of these ecosystems. So what we wanted to do in this study was to see if we could implement a new parameterization of foliar stoichiometry that changes over time in response to CO2, and what that would do to some of the carbon cycling responses and other biogeochemical responses in the community land model. So we generated this new equation based off of some of those phase meta-analyses as well as LTER syntheses to project the leaf carbon to nitrogen ratio as a function of atmospheric CO2, which we implemented into CLM and ran that offline with land-only DSWP3 forcing and an SSP370 anomaly. Now, you might be familiar with a flexible C to N term that is already in CLM5. However, the FUN module that controls the nitrogen cycling has fixed plant functional type specific C to N values, and that sort of outweighs the flexible parameterization in CLM. And so that means that the foliar C to N values don't currently really change over time very much in CLM, which you can see here in this orange line at the bottom of this plot. So that's our fixed foliar C to N scenario with the current parameterization of CLM. And this blue line, flex, is our new parameterization with that CO2-driven foliar C to N, which then goes up over time out through the end of the century. So this essentially shows that our new parameterization was doing what we hoped it would do by increasing the foliar C to N as CO2 changes in the model. And in that fixed foliar C to N scenario, there are different C to N values specific to each plant functional type. So those range from about 20 to 50 across the globe. However, those don't really change over the course of the simulation. However, in looking at the difference of the fixed and flex scenarios by the end of the century, you can see that there's an increase of about 20 in the C to N values across most of the PFTs, showing again that our new parameterization is doing what we had hoped it would do in the model. Now, we wanted to first see how that would then influence some of the carbon cycling variables that were of interest to us. First, thinking about the cumulative land carbon uptake. This looks at the land carbon sink over the historical period first. You can see our fixed scenario here in orange compared to the flexible scenario in blue. Both scenarios were well within observationally derived data from the Global Carbon Project, which is in black, and the gray area is the confidence interval. They were also within the confidence interval of an 11-member ensemble of CMIP6 data, which is in purple. So this suggests that both our fixed and flexible scenarios are plausible scenarios to use to project the land carbon sink. However, when we look at these out through the end of the century, they really strongly diverge, with our flexible scenario being about 200 petagrams of carbon less than the fixed C to N scenario, suggesting that how we're representing foliar carbon to nitrogen in the model is likely to have really major implications for projections of the land carbon sink. Now, this change in carbon uptake was not evenly distributed across the globe. So this map looks at the difference in the fixed and the flex line by the end of the century spatially. You can see that there are the greatest reductions in the land carbon sink in tropical regions, as well as in some boreal regions. And this owes largely to a reduction in photosynthetic capacity in the model. So this is demonstrated here for MPP on the y-axis, which is reduced pretty strongly by the end of the century in that flexible scenario, again shown in blue. We also showed similar responses for GPP, leaf area index, and heterotrophic respiration, which I won't show here, but if you are interested in those data, I have them elsewhere and can share them later. This change in photosynthetic capacity was similarly spatially distributed as changes to the land carbon sink. So this again shows a difference between the fixed and the flex line in the last plot across the globe, with the greatest changes being in tropical regions again. And this actually had some really interesting implications for biophysical cycling that I hadn't really necessarily thought a lot about before running this experiment. But these changes to MPP and vegetation productivity specifically had really major implications on the hydrologic cycle. So we saw reductions in evapotranspiration across latitudes in our flexible scenario, demonstrated here in the left-hand plot in the blue line. And that was matched by a similar increase in runoff in the flexible scenario on the right-hand side. And this was again strongest in tropical regions, which is likely to have really important ramifications for climate, given the role of tropical evapotranspiration, especially in driving large-scale precipitation patterns. We did also see that there were changes in nitrogen cycling in our flexible scenario. So this demonstrates that there was a reduction in net nitrogen mineralization rates. Nitrogen cycling rates were generally lower in the flex scenario, which again is shown here in blue. This mostly reflects that change in productivity that I showed you earlier, because the reduction in productivity reduces the vegetation nitrogen demand, and that then reduces nitrogen cycling rates. However, this doesn't necessarily allow us to easily parse whether there are some below ground feedbacks going on that may be further changing productivity. So currently the model doesn't represent flexible soil stoichiometry. So this doesn't necessarily allow us to see if there is a feedback between changes in foliar stoichiometry and below ground nitrogen cycling and soil stoichiometry that could further lead back into changes in productivity. So that's one of the next steps that I hope to address with this research, and hopefully we'll continue investigating that through potentially through using the Mimics model, and see if we can examine some of those feedbacks a little further. Another next step that I would be curious to hear your thoughts on for this research is whether or not this parameterization might be useful in CTSM, because it is not currently representing this sort of directional change in foliar stoichiometry, but hopefully at some point in the future would be a representation or represented by the model. Would this be sort of a useful interim step to allow us to examine some potential outcomes of this directional change in foliar stoichiometry that's being observed in a lot of Earth's ecosystems? So I'd be curious to hear your thoughts on this, as well as some of the other future directions of this research. And I would like to thank a lot of people who have really helped in developing this research and helping me bring a lot of empirical studies that I am sort of have more of a background into the community land model. And I would be happy to hear your questions or any thoughts you have on some of the future directions of this. Well, thank you.
We have time for questions. I see Rosie has raised her hand. Do you want to go ahead, Rosie?
Yeah. Hi. Thanks for that. That's really interesting. So I guess I was so as you alluded to, it's not strictly fixed, the C to N ratio in Salem 5. We have this this function which changes the C to N ratio as a function of how expensive it is for the plants to get nitrogen out of the soil, as is the kind of concept embedded in the fund model, right? So the original fund model was devised with a fixed C to N ratio, and that was easy to solve. But to kind of make it kind of compatible with this flex CM, we introduced this other function, and we found in the sort of the parameter sensitivity paper from CLM5 that the parameters of that model were the CO2 response to the model was sensitive to the parameters of that system. So I guess my question is it possible to use the same concept to get the same result as you have with your empirical function, using some kind of scheme which is tied to the cost of the nitrogen from the soil?
I think that, as I understand it, that would kind of be a goal, so that the C to N does change as a plant exchange cost. But because there is something that is currently sort of overriding the ability of the C to N to be flexible in CLM, it's not necessarily performing that, which is why we introduced this sort of empirically derived function, if I'm getting that right.
Yeah, so it doesn't override it. It's parameterized, as you've illustrated. It's parameterized such that it's not very variable. So that it's quite a lot.
Yeah.
It's quite a big difference between being invariant and not very variable.
Yeah.
So
yeah.
So I guess what I take from your study is that's parameterized on the insensitive side. So I guess I'm interested in whether it's possible to parameterize, if not the function we have now, which is a little ad hoc, admittedly, but a function which is tied to the cost of nitrogen from the soil. Because you would imagine that would be the driving factor of this flexible stoichiometry, right? Is that you can't just keep taking up as much nitrogen as you want. It gets more expensive as CO2 fertilization carries on. And so, yeah, I think that'd be interesting. And we can talk offline if you like. But
yeah, that would be cool. I think that there are definitely more parameters that could be represented, and more sort of complex ways of representing it, so that it's more variable than it currently is, and not just strictly like a function of only CO2, but also potentially nitrogen demand and nitrogen cost. But we took a fairly simplistic route for this first step and just based it on CO2. But I'd be curious to hear how you might modify that, certainly.
Cool. Thanks.
Thank you.
We have time for another question.
I have one question. In your time series, it seems like there's some sort of repeated forcing that causes like sort of a W shape every, 15 years or so. What is going on there?
Yeah, that has to do with how the model iterates over, I think, historical data. I am bad at explaining this, but I have had Will explain this to me before, if he's there. And essentially, like, I don't know if I can do a good job of explaining it very well.
Do you want help?
Will, are you there? Yeah.
So we just cycle over the last, I think it is 15 years of the GSW P3 forcing, and then apply an anomaly that kind of matches the change in driver variables that CESM2 represented. So that way we're kind of able to smoothly transition from the historical period to the SSP. But you do get that kind of periodic oscillation because we are cycling over the climatology.
So it's just like a bad year in the climatology that keeps coming back up again.
Yep, keeps happening. Yeah.
Thank you.
Great, okay, so we figured out the confusion as there were multiple versions of the schedule with different speakers listed for the last talk. And so we're actually having Jen Ying Fang presenting. And so I'm seeing we're not seeing it full screen yet. If you want to try to go ahead and do that.
Okay. Is it working right now?
Yes, that looks good. So, yep.
Okay.
Thanks for your
Okay.
accommodation of the mix-up, and go ahead.
Okay. Thank you so much. So, hello everyone. My name is Jianing Fang, and I'm a second-year PhD student working with Professor Pierre Gentin at Columbia University. So, first of all, I would like to apologize for all the confusions in the scheduling. And today I'll be presenting this talk on behalf of Professor Gentin as well as Dr. Julian, who is a postdoc in our group also working on this project. So the topic of this talk today will be reconstruction of a long-term spatially contiguous solar-induced fluorescence data over 1982 to 2021. And the main motivation for this project, and in particular its implication for land surface modeling, is that many times when it comes to monitoring long-term vegetation dynamics, we do not have very good global constraints. We have satellite observations from, for example, AVHR back in the 1980s, the early 1980s. However, for those earlier satellite technologies, there's often uncertainties in these data sets due to orbital drifts and also the inherent problems of using vegetation indices. So here is just an example of a paper published in Science trying to claim that there's a recent global decline of CO2 fertilization on vegetation photosynthesis. But after this paper was published, there have been several comments on this paper saying that maybe we should be a little bit skeptical about the results because for these earlier decades, the paper used data from AVHR, but there were known issues of orbital drifts due to the lack of onboard calibration and propulsion of these earlier satellites. And also, there's an issue of whether these optical vegetation indices can actually represent photosynthesis or not, or whether they are actually reflecting, for example, canopy structure change or maybe changes in land use, land cover. So in order to address this issue, we believe that there is a need for a long-term solar-induced fluorescence product. Solar-induced fluorescence might be helpful in this case because it is a signal that is more closely related to the physiological response of vegetation photosynthesis. So maybe it is a proxy that is closer to the biophysiological effects they want to capture. And previous studies have shown that there's a great potential of using SIF to monitoring GPP, but the challenge is that the satellite observed SIF soundings are usually pretty sparse in space and time, and we have a relatively short records. And when it comes to higher quality SIF, our available time series is just even shorter. And one way of addressing this issue is to use neural networks or other deep learning techniques to reconstruct global contiguous SIF by relying on some of this statistical relationships between SIF and reflectance, because we can monitor reflectance for a relatively longer period, and also reflectance data sets are spatially contiguous. And there have been multiple successful attempts of reconstructing these globally contiguous SIF, but the question remains the extent to which that these reconstructed SIF can be actually attributed to physiological signals. And if we were to extend these reconstructed SIF to, for example, early 1980s, then we need to use earlier satellites records of reflectance. But that again, is a challenging topic because we don't know how much confidence we have in these earlier satellites. And also, when it comes to AVHR, there are only two bands, like broader bands of reflectance in the red and near infrared regions. Whereas for many of these reconstructed SIFs, they use the first four bands of MODIS. So it is unclear whether we can have a reliable reconstruction of solar-induced fluorescence all the way back to the early 1980s. But here we decided to take on this challenge, and we want to see how far we can go in this direction. So in order to make sure that we have some confidence in the AVHR dataset, we apply a relatively systematic approach to calibrate AVHR against MODIS. So we apply all the relevant quality flag in the LTDR data, and also we apply an orbital drift correction. So basically we remove the potential effects of solar zenith angle on the AVHR reflectance data using a method that was previously found to be successful in a paper by Jiang et al. In 2018. And after orbital correcting that AVHR dataset, we combine it with MODIS and we cross-calibrate it with MODIS. And here we use a double correction procedure in order to leverage both the temporal and spatial correlational structures between AVHR and MODIS. So first we apply a pixel-wise linear model, and that's mainly based on a local correlational structure from the temporal domain. And we build that linear model to first apply the first layer of correction. But we think that there might be other systematic biases between the two data sets due to, for example, differences in reflectance bands, different atmospheric calibration procedures. So the next stage, we apply a global calibration using a machine learning model, and we use aerosol optical depth, snow depth, cloud cover, elevation, and aridity indexes predictors. And that is to leverage the spatial correlational structure between the two data sets. And we apply it on the residual so that we fit a model based on residual, and then we correct it again to match the AVHR record. And after we build a consistent reflecting data set, we use the same methodology as in the CESM paper by Dr. Yao Zhang. And then we built a neural network that maps the reflectance, the long-term reflectance data set to OCO2 SIF sendings. And we aggregate the SIF sendings to 0.05 degrees in order to reduce the noises in the SIF retrievals. And then we train this neural network, and we also include cosine solar zenith angle. This is a proxy of radiation. And after training this model and validating it on a held out data set, we apply it to generate the long-term C product. And we have two versions. One version is the clear instantaneous SIF. So that is based on the predicted theoretical satellite overpass time of OCO2. And another version is to apply a daily correction factor to correct it based on the average SIF on in a particular day, based on this integral of cosine solar zenith angle. And we found that our model generally performed pretty well in terms of reconstructing the global SIF relationship. And notice that here, although we only use 2 bands for the reconstructed reflectance data set, they actually achieved a performance that is on par with the previous study by Yao Zhang that uses the first 4 bands of the MODIS. And we also examined the potential residual orbital effects by validating our data set at those pseudo-invariant calibration sites. So these are desert locations in Sahara or the Arab Peninsula that theoretically there shouldn't be any vegetation there. And so any trends that we observe should be due to some systematic biases or noises. And we found that there's little correlation between these signal at the PICS sites and the global anomaly of the SIF. So that is reassuring, saying that we have addressed most of the orbital effects. And after that, we also compared our new data set with several existing reconstructed SIF data set. And in general, it is pretty consistent in the temporal domain. And it's showing a consistent increase, a consistent greening of vegetation during this period from 1982 to 2020. And also, we noticed that there weren't many systematic biases between the MODIS and AVHR period after the calibration during this overlap period between 2000 and 2002 across different vegetation heights. And we found that there's a greater increase in the global SIF trend in the 2001 to 2021 period than the earlier period. And mainly we see a lot of greening up in Eastern Asia, in the Indian subcontinent, and we see that there is some browning trends in the Eastern Amazon that is corresponding to deforestation. We also noticed that okay, thank you so much. And we also noticed that our data set is generally consistent with previous reconstructed SIF data sets in terms of both trend as well as phenology shifts. And when comparing our data sets with vegetation indices, we found that there's generally a stronger increase in the overall SIF anomaly during this period, but we see a slightly smaller phenological shifts in the boreal region. And that is potential because SIF is better able to capture the physiological effects. And in those boreal regions, as a previous study pointed out, that maybe this smaller shifts in the SIF is due to light limitation. We also found that our product has the potential of capturing vegetation responses to drought events. So we look into various significant drought events, regional drought events. We found that our data set is able to capture this decrease in photosynthesis. So our data set will be made publicly available in May this year, and there's a trial version that if you're interested, you can send us an email and we will give you access to a preliminary data release. So note that for the land modeling community, our model has the potential, our data has the potential of accessing long-term vegetation productivity in response to climate, CO2, and also land use land cover change. It can also be used as a potential benchmark data set for comparing Earth system model results, as well as assimilating into global biogeochemical models. So thank you very much, and that's the end of our presentation. Any questions will be welcome.
Great, we have time for a question. We'll go to Gretchen first, and then we'll do Peter.
So when you were showing the sort of the validation for your product, it looked like there were about 2 units of dynamic range. Yeah, the previous slide that I think it's the one previous, 2 units of dynamic variability on the SIF, and it seemed like the scatter about the line was at least like 1.5 units of dynamic variability. So, I know SIF suffers from imprecision, but that would suggest to me that there's something problematic about the spatiotemporal scales that you're providing the data at, that there has to be some recommendation to bin or aggregate the data to deal with that imprecision. Can you comment on that a little bit?
Oh yes, so that's a very good comment. And indeed, we see that during the MODIS period, if you look at the anomaly, they are generally consistent with each other, the reconstructed SIF. And that's not surprising because they actually use the same input and output data set. So all of these use the OCO2 SIF, and all of these use MODIS as predictors. So that's why the interannual anomaly are consistent. But when it comes to the absolute change, that can be different due to the differences in the algorithms, and it can also be due to the different ways, like some of the data gaps in the data set. So when I see people do assimilation of these data sets, they generally look at the normalized. So I think there's more information contained in the absolute in this like relative interannual anomaly than the absolute signal.
Great. I think in the interest of time, we'll need to move on. So Peter, you could add a question to the chat if you like. And I saw there was another question for you there in the chat if you want to answer it. Next up, we're going to have James King, who is online. James, are you there? Great. So I think we need to stop sharing one screen and then we can start sharing the other.
Oh, okay.
James, do you want to go ahead and try to share? Oh, I'm not sure if we can hear you either. No, we're not able to hear you yet. Nope. I see you talking and I saw you mute and unmute, but we still don't have audio. Audio was working yesterday. Any ideas, anyone? You have a suggestion for
tested with him just a little while ago
and
and he couldn't get his mic to work, so.
Oh, okay. Okay, should we do another switch here potentially in the schedule and then come back to James after that, as long as we have our next speaker? Would they, Shuyan Gao, are you there?
Yeah, sure. Can you hear me?
Yeah, are you able to present now? Would that work for you?
Yeah, just I can present now.
Okay, thanks for everybody's flexibility today. So it looks like you should be able to go ahead and share your screen now.
Can you see my screen?
And you're not in, there you go, that's full screen mode. So Shuyan is going to be talking about an exploration of novel carbon dioxide removal option lighting of tropical forests at night. So go ahead.
Okay, thanks. Hello, everybody. My name is Xueyuan Gao. I'm a PhD student at the University of Maryland, College Park. And today I'll be presenting my work on exploration of a novel carbon dioxide removal option lighting up tropical forests at night, and focus on the implications for nature-based climate solutions. To give you a more complete story, I will talk about how I came up with this idea from the very beginning. So this is a water drainage pool in the basement of my house. And there's only one light bulb in this room. And you can see this light bulb makes a shadow in the pool. And in the shadow area, there grows no lichen. But outside of the shadow, there grows a lot of lichen. And it made me think of the importance of light in determining the growth of plant. So initially, I was thinking, can we light up the whole dark side of the earth to increase the carbon uptake of the whole biosphere? So I came up with two plans. The first is to launch visible light lasers to the geostationary orbit. So this is a common situation, and this is the dark side of the Earth. And if you launch visible light lasers to the geostationary orbit, you should be able to provide some artificial lighting to this dark side of the Earth. This is a radiation distribution on top of atmosphere, similar to the BioMath. And I use Stephen Boltzmann law to roughly estimate the temperature increase. So basically this plan resulted in a temperature increase around 22 degrees Celsius or Kelvin. And the second plan is just to launch a set of space mirrors that orbit the big circle of the Earth to reflect the sunlight to the dark side. And this is radiation distribution on top of atmosphere simulated by using MATLAB. And this is the rough estimation of temperature increase. So the temperature increase depends on this angle. So the larger this angle is, the larger the area will be, it's going to be illuminated will be. So you can see there's still a very high temperature increase due to this plan. And the reason is most of the radiation is absorbed by the land surface for heating. So this was when I shifted the idea to forests, because theoretically, most part of the solar radiation that reaches the forest surface will be used for photosynthesis or used for chemical energy storage. So my work is just to explore the carbon cycle responses to this plan, lighting up tropical forests at night via LAM networks about the forest canopy, and to quantify the influence on carbon sequestration, local climate, eco-environment, and technical and economic feasibility. I conducted numerical experiments by fully coupled CESM2, and this work was supported by NCAR high-performance computing platform. So the nominal horizontal resolution is 1 degree. Tropical forests are defined by broadleaf evergreen, tree area percentage larger than 60%. And in CESM2, the solar radiation consists of 4 components: direct visible light, diffuse visible light, direct near infrared, and diffuse near infrared. So in the experiment, all the other 3 components were specified to be 0. The diffuse visible light was specified to be 200 watt per meter squares. And the reason for this, choosing this specific number, will be introduced later. So this is the methodology framework. The whole experiment consists of a series of sub-experiments. First is 14 years historical simulation. And starting from 2015, I did a series of lighting experiment. So first is 24-hour experiment to find the appropriate lighting power. So this is so from this stage of experiment, I decided to choose 200 watt per meter square, and then followed by a 16-year lighting experiment. And at 2031, I stopped the lighting experiment, then kept running the model for another 20 years to see how the carbon cycle and climate responded to the experiment termination. This is 20 years. And all this experiment were along with control simulation, and also in 2 members to estimate the uncertainties. All right, so here, due to the time limit, I omitted the 24-hour experiment results. But if you're interested, we can definitely talk about this 24-hour experiment results in detail later. So here I'm going to show you the 16-year lighting experiment results, how tropical forests responded to this lighting experiment. So you can see that the GPP and autotrophic respiration responded pretty quickly to the lighting experiment, and it increased significantly. While at the same time, the heterotrophic respiration or soil respiration gradually increased, but in a much lower rate. And as a result, the net carbon uptake of tropical forests was elevated to a pretty high level at the start of the lighting experiment, but then gradually decreased because of the increase of soil respiration. And local air temperature increased along with the local precipitation and soil moisture. And as a result, the global CO2 concentration decreased. And the global average air temperature increasing rate also decreased due to the experiment. So this is the global tropical forest carbon flux and climate responses to the 16-year lighting experiment. And as I said, then I stopped the lighting experiment and kept running the model for another 20 years. Then let's look at the tropical forest responses to this experiment termination. So when you stop the lighting experiment, the GPP and autotrophic respiration dropped down quickly, while soil respiration started decreasing, but also at a much lower rate than GPP and plant respiration. So as a result, the net carbon uptake, the tropical forest turned into a net carbon source at the termination of the lighting experiment. And local air temperature came back to the control level, as well as the precipitation and soil moisture. So because tropical forests now started releasing carbon dioxide into the atmosphere, the global CO2 concentration started increasing again. But overall, the global average air temperature is still lower than the control simulation. And then I look at where did the net absorbed carbon go. So there are three major carbon pools in tropical forests: vegetation carbon pool, coarse woody debris and litter carbon pool, and then soil carbon pool. So you can see that most of the carbon, most of the net absorbed carbon went into the vegetation carbon pool. But since the lighting experiment terminated, the vegetation carbon pool and coarse woody debris and litter carbon pool started decreasing, started shrinking. But the soil organic matter carbon pool kept increasing for a little while until it started decreasing, because the carbon from other from coarse woody debris and litter carbon pool kept entering this soil organic matter carbon pool, even if we stopped the light experiment. So several discussion about these results. First is the ecosystem level field experiments are needed. So physiological responses of tropical trees to longer photo periods at the ecosystem level remain the one of the biggest uncertainties. And the tree growth might be limited by nutrient and water supply. So this ecosystem level field experiments are needed to better understand the tropical forest ecosystem responses. The second discussion point is CESM2 overestimated local air temperature increases due to the omission of chemical energy stored during photosynthesis. So this is the canopy energy conservation or energy equation used to calculate temperature. So this is solar radiation, long wave radiation, sensible heat, and latent heat. So this is energy equation used to calculate temperature. However, in CESM2 and other modern Earth system models, the chemical energy that is stored during photosynthesis and released by respiration is ignored, and the net chemical energy usually amounts to less than 1% of absorbed insolation. So this is the normal condition. However, in our lighting experiment, 16-year lighting experiment, 17% of absorbed insolation was fixed in the ecosystem as chemical energy and didn't contribute to local air temperature increase. And the model failed to exclude this chemical energy storage from the energy equation. So the model overestimated the local temperature increase. And the implication of this point is the temperature simulation results, and especially vegetation temperature simulation results, should be treated carefully when Earth system models are used to do experiments related to solar radiation modifications. Then the third discussion point is the post-action CO2 outgassing from tropical forests. So how to understand this phenomena? During the control simulation period, you see the vegetative primary productivity, or MPP, is on a similar level of soil respiration. So you see this green line represent the net ecosystem productivity. However, when you give additional lighting to a forest ecosystem, the productivity of vegetation increased significantly and in a much faster rate than soil respiration. So soil respiration also increased, but in a much lower rate. And as a result, the net carbon uptake increased. Well, however, when you stop the artificial lighting, the GPP decreased, and soil respiration also started decreasing, but in a much lower rate. It started the whole ecosystem turn into a carbon source. And this is pretty similar to, just imagine if you take stimulants, the stimulants are gonna enhance your body function. But when stimulants lose effect, it's gonna destroy your body function. So I just name it stimulant effect. So giving forest ecosystem additional lighting, it's similar to you're giving stimulants to human bodies.
So we're well into time if you're able to wrap up now.
Okay, so sorry, very quickly. So you can also observe similar phenomenon in overshoot scenario simulations and on the free air carbon dioxide enrichment experiments. So it implicates that CO2 removal methods focused on enhancing ecosystem carbon sequestration by altering environmental factors in the short term could induce this post-action CO2 outgassing. Very quickly, conclusions. I think the first is implications for Earth system model users. The temperature simulation results should be treated carefully when Earth system models are used to do experiments related to solar radiation modifications, and implications for nature-based climate solutions, enhancing land ecosystem carbon sequestration by changing environmental factors might be an inefficient approach. And finally, for geoengineering measures, it's important to study the post-geoengineering reactions. Well, I think that's it. Finally, I want to say this article has been published in Earth System Dynamics, and I'll be giving a departmental seminar tomorrow. So just feel free to reach out to me. We're going to discuss a lot more details. So you can reach out to me for a Zoom link. Thanks.
If you want to go ahead and stop sharing your screen, we can take one question while we have James getting set up. We have one question online from Sanjeev. It says, great academic exercise. Do plants need to sleep? I guess you can go ahead and answer that in the chat if you want to.
Oh, it's in the chat box?
Yeah, or just go ahead and give us a verbal answer quickly, and we'll, James, you can go ahead and start sharing your slides. Do you think plants need to sleep?
Does plant need sleep? Yes. Well, I think so. This is mainly really about the physiological responses to plants, and I believe it needs more studies about this one, like the physiological responses, before you really launch such experiments in reality.
Great, thank you. Really interesting to think about very different situations. James.
Thanks so much.
Let's see. We see you. Can we hear you this time? You look muted at the moment. There we go.
Hello.
Excellent.
Yeah, sorry, my voice is probably a disappointment after all that, but there you go. Thanks very much for your patience. I'll just start my presentation.
Excellent. That looks good.
Oh,
We
good.
see you, we hear you, and we see your slides. So go ahead. Go ahead.
Yeah, perfect. Thank you very much. My name is James King. I'm a postdoc at the University of Sheffield here in the UK. And today I'm going to talk to you about some work we've been doing with CLM5 and with the broader CESM2 model, looking at the atmospheric and climate and environmental implications of tree planting as a carbon dioxide removal strategy. So firstly, just acknowledge my colleagues James and Maria. Maria leading the project, and also Peter Lawrence, who we've been working with at NCAR, and also broadly the members of the Land Model Working Group. I was fortunate to spend some time at NCAR over summer last year and had some really productive discussions. And thanks to everyone who's contributed to these fantastic modelling tools. So why are we interested in trees? Tree planting on a global scale has really attracted a lot of attention from governments, NGOs, and civil society as a strategy to take carbon dioxide out of the atmosphere. So lots of countries have made national commitments, usually with large and suspiciously round numbers. We're going to plant 2 billion trees, we're going to plant 3 billion trees. There are also international agreements such as the Bonn Challenge, countries agreeing to restore degraded forest. And also, more recently, the Glasgow Declaration as part of last year's COP made big commitments towards landscape preservation and restoration. And it makes sense, you know, why invent direct air capture if you can just use a tree? But obviously, trees have more impact on the environment beyond just absorbing carbon. And some of the motivation for this work is the realization that a lot of big splashy papers talking about tree planting have focused mainly on how much carbon will they absorb. And there's been less attention, although that's a picture that's changing now, on the climatic and environmental impacts of trees, which are numerous. Obviously, trees affect evapotranspiration, they affect albedo, so there's implications there for surface energy balance. Trees emit BVOCs, such as isoprene, monoterpenes, sesquiterpenes, which have a variety of complex interactions with atmospheric chemistry, potentially enhancing the lifetime of methane. Downstream, BVOCs produce aerosols, which then interact with clouds and interact with radiation. We also see via nitrogen cycle impact on ozone, which obviously high up in the atmosphere is a good thing, but in the troposphere is a bad thing. And from a land surface perspective, a shift from grassland or cropland to trees could be expected to increase water stress, decrease soil moisture. So there's questions there for the plausibility of tree planting as a strategy as well. I'm going to talk a bit about land stuff today. I will add the caveat that I'm not by training a land surface expert. So one of the reasons that I'm talking to this distinguished group here is to kind of ask for feedback and pointers, see if we're on the right track. So how are we investigating global tree planting commitments? So we're using CESM on, we've successfully ported the model to Archer 2, which is the new British flagship HPC system. It's very shiny, it's very fast. It also doesn't work a lot of the time, but we're working on that. For this particular set of experiments, we're running the model fully coupled, so sort of everything on. We have the active ocean. CLM5 is running in BGC crop configuration. In the atmosphere, we run the TS1 atmospheric chemistry scheme to look at aerosol oxidation and downstream impacts. We have 3 experiments, all of which follow SSP1 2.6 in terms of greenhouse gas concentrations and sort of anthropogenic emissions. The experiments differ in the land use. So we have a base case which follows the SSP1 2.6. Our max forest scenario, which came out of a piece of work that Peter Lawrence did, which I'll talk about in a minute, and a control where we hold land use and land cover constant at 2015 levels. We run the model over the period of 2015 to 2100, using obviously spun up initial conditions. And we will be running 3 ensemble members, so that's 3 times 3 runs, eventually, once they've found some more storage for us to save all that output. The max forest scenario, as developed by Peter, is we think a quite significant advance on a lot of the studies that you see looking at global tree planting, which are often a little more straightforward. You know, we deforest the globe or we plant trees everywhere on the globe and we look at what the impacts are. Here we have a transient land use land cover scenario in which tree cover is allowed to expand following a set of constraints. This is what it looks like on the globe. So that kind of cycle for a few moments, and the color bar here is the percentage of natural vegetation made up of tree PFTs. Those of you obviously know how CLM5 apportions the land. And we can see that essentially in this scenario, existing tree cover expands, and primarily we see that expansion in tropical rainforests, but we also see significant expansion in North America, Europe, South, and parts of East and South Asia. You'll note that we avoid planting trees north of about 60 degrees north to account for the potential negative impacts of decreasing albedo when you plant dark conifer trees on what was previously scrubland. If we look at this scenario in context, so on this plot here, the max forest scenario is the dotted line. The solid lines are the various SSP scenarios. And we compare the max forest scenario, we see it fits in favorably with policy commitments that have been announced. So that it fits in nicely with the bond challenge. GRC there is a database of global reforestation and restoration commitments up to 2050. And we see that the max forest scenario on a global scale is slap bang in the middle of that. Forest expansion is constrained by climatic suitability, so you don't plant trees in deserts where they won't grow. We take into account the demand for agricultural land by holding that constant at 2015 levels with a few minor adjustments. And tree planting peaks in mid-century, which is aligning with the commitments and sort of asymptotes towards 2100. If we look at the scenario regionally, we can see that the majority of the tree planting in the scenario takes place in tropical rainforests. In more temperate environments such as Europe, it's comparable to SSP1. And this is quite a good thing, we think, because the tropical rainforests, you don't have so much of a water limitation problem. The albedo problem essentially is negated by latent heat release, and the biodiversity benefits are substantial. So this is a great bit of work by Peter that he's kindly allowed us to use and kind of run with a little. So what happens when we run this scenario in the model? For a start, we see across the globe increases in net primary production or net primary productivity, associated with a shift to more tree cover. This is associated with carbon dioxide removal, so concentrations of CO2 are lower in the max forest case than in the base and the no land use cases. As with most of the variables, the predominant effect here is in the tropical rainforests, but we do also see increases in NPP in North America and Southeast Asia as well, relative to the other scenarios. Surface temperature is generally lower in the max forest scenario than in the base and the no land use scenarios. As a result of that kind of latent heat cooling effect we see in the tropics, you can see that the most significant impact in the Congo Basin there, kind of a headline figure, if you like, is that the expansion of forest cover in this scenario, which is proportionally greatest in that region, actually almost removes the climate change signal if you look at that purely in terms of global warming at the surface. So there are substantial implications of global tree planting at the more local scale for mitigating against the temperature effects of global warming. And this is just kind of associated with the latent heat release from a more photosynthetically active biosphere in these regions. We don't see as much of an impact in the temperate zones, but again, if you look at the Amazon and the Congo Basin, substantially higher evapotranspiration per unit area in the afforested tropics. Here's where I'm kind of going towards the bounds of how much I understand about how the land model works. So I'm interested to hear feedback on these sorts of results. If we look at the difference in 2095 here between the max forest and the SSP1 cases and the no land use case, we see, looking at the right plot here mostly, statistically significant decreases around the expanded forest regions in the vegetation water potential. And if we plot this on a time series, we can see that those are fairly universally spread out across our region. So a decrease in vegetation water potential, that quantity is becoming more negative. And my understanding of this quantity is that this reflects an increase in the water stress of the vegetation in CLM5, which would reflect the increased demand for water from trees as opposed to grasses or shrub PFTs. So this kind of speaks to the viability of this strategy. We've seen that it, from a sort of temperature perspective, could have some real benefits, absent any other benefits we might talk about. But when we look at a pretty significant increase in the water stress, that does lead us to question the viability of this sort of approach.
You're at 10 minutes.
I'm at 10 minutes, perfect. Okay, I'll wrap up fairly quickly. We also see, again, primarily in the Congo, substantial decreases in soil moisture associated with the max forest scenario. The picture for runoff is not so clear, but then in SSP1 2.6, very few of these regions see a significant change in precipitation. So that's kind of more bound up in what's going on in the atmosphere. Other stuff we're doing includes looking at atmospheric dynamics. So bottom left there shows a significant northward movement of the Hadley circulation in response to more trees in the northern hemisphere, where there's more land. We're looking at air quality and atmospheric chemistry, so the isoprene reactions associated with BVOC emissions from trees substantially increase PM2.5 concentrations at the surface in the max forest scenario, which is obviously bad for human health. So there's more that's being looked at there. So we're looking at this scenario and the policy of reforestation from lots of different perspectives. So yeah, that's where we are at the moment. CDR potential and cooling do certainly exist if you have a global scale afforestation, reforestation and forest restoration pledge that's in line with policies. But there is also increased water stress, which has kind of implications for the viability of those plants if it wasn't in a scenario where we were sort of imposing them. Other implications are under investigation. Welcome any comments on what we're doing so far. Thanks a lot.
We have time for questions. I actually have a question. You said it was fully coupled, but I wasn't actually sure if that meant that you had prognostic atmospheric CO2. I'm guessing probably not, but maybe you did. And either way, could you comment on what the carbon feedbacks might have been, because you're changing photosynthesis at the same time. So you're talking about changes in surface temperature. I'm wondering if those also include the impacts of any carbon concentration feedbacks.
So yeah, the carbon in the atmosphere is prescribed following SSPs, so it's not an emissions driven. So effectively, the runs that we do have no impact on the CO2 in the atmosphere. You know, the land draws down carbon, but the carbon in the atmosphere is prescribed, which obviously is a limitation of this kind of study. And we're doing some work with a simplified UK model called FAIR to kind of try and constrain that more effectively. We haven't as yet, partially for this reason, our setup, it makes it quite tricky to work out what would be the cooling effect from changes in the carbon cycle from enhanced biosphere carbon directly. We can make indirect calculations based on the size of that carbon sink, or the size of the increase in that carbon sink, and look at what the reductions in atmospheric CO2 would be if we did have prognostic CO2, which is something we're working on at the moment. It's small but not insignificant if you compare that to SSP1, which obviously is a scenario which we meet the Paris targets anyway. So yeah, that's a very good question. I'm aware that colleagues at NCAR are working on slightly more sophisticated model setups than what we have here, by doing emissions driven rather than concentration runs. And I think that's a very exciting tool to answer that question a lot better. Peter, hello. Do the BVOCs impact low clouds in the re/afforested regions? Slightly. It's a very localized picture. There's some increase in low cloud over tropical Africa, but globally the cloud signal is dominated by the SST variability. So that's a question we're working on with our ensembles effectively. It's tricky to isolate cloud signal amongst cloud noise, as is often the case with a single set of ensembles. But the next set of ensembles are in the works and starting to tee up and run. And hopefully we'll have a clearer picture of the cloud response once we have those ensembles.
We could take one more question if there's another question.
Happy to. Otherwise, I'm aware it's coffee time in Colorado.
We'll do one more. So, Crystal, go ahead.
Cool.
Thanks. Interesting talk. I'm just wondering, to first order, if you add more water vapor to the atmosphere from extra transpiration, are you going to add additional regional warming at some level, even if the surface itself cools?
Yes. So you would expect to see some impact on the sort of the surface energy balance. We are currently running, because it's quite tricky to extract that direct impact of water vapor amongst a scenario in which we're allowing the ocean to evolve. So that tends to be what is driving the atmospheric moisture is an SST effect rather than a land surface effect. So we'll have clearer answers on that, I think, once we've done the ensembles. But the picture that's emerging from some work we're doing with a sort of offline cloud and water-based radiative forcing calculations is it's not especially significant a signal outside of the Congo Basin in Africa. We don't really see a signal anywhere else, which is interesting and deserves more interrogation, I think.
Great, well, thanks very much. And we are up for our break next. For folks online, there is an online breakout group that Elizabeth sent out. You're welcome to go there and chat. For folks here, we will have refreshments outside the room, and we're reconvening
10:20.
at 10:20.
25 minutes.
25 minutes, we'll see you back in here. we'll get started in just a minute, Charlie.
Great. And you all can hear me in the room?
Can hear you and see your slides.
Great. And if I advance my slides, that you see that?
Kick off our second session of the morning with Charlie Coven, who's presenting remotely on the zero emissions commitment. So Charlie, do you want to go ahead?
Thanks, Gretchen. Yeah, so I'm going to give a talk today. Tell much of the zero emissions commitment occurs before reaching net zero emissions, which is maybe a confusing title, but hopefully I'll explain it to you. And yeah, so I'm going to start off. The motivation for this comes from this figure, which I think is sort of arguably like the most important figure in our field of sort of coupled carbon climate, which shows the linearity and the path dependence or path independence of the proportionality of global warming to cumulative emissions, right? So this relationship that warming is proportional to cumulative emissions, is the basis of a lot of policy. In particular, the thing that motivates this is this kind of cryptic last phrase in the caption for the IPCC AR6 for Group 1 summary for policymakers, the version of this, where they chose to put it out only to 2050. And the reason given there is that there's limited evidence supporting the quantitative application of the TCRE, which is the transient climate response to emissions, which is this proportionality, to estimate temperature evolution under net negative CO2 emissions. So what's going on there? Why is there only limited evidence? And why is this sort of put out there as this caveat? So I was curious about that, and so that led to this stuff. Okay, so what's going on with why this TCRE relationship might not hold under net negative emissions? This idea comes from this paper led by Kirsten Zickfeld in 2016, where they did a 1% per year concentration reversal experiment, and what they found is under that that there's this systematic asymmetry between this relationship between the temperature anomaly and the cumulative CO2 emissions under positive under negative emissions, right? So after you get to net zero and go back, there's this consistent positive bias, and you can see that in the CMIP6 CDR-MIP experiments as well. That the CMIP6 model is also this consistent positive asymmetry, so that after going to negative emissions, there's still the temperature is higher for given cumulative emissions than in the upswing. So there might be like this consistent bias after net zero. And so that's from these idealized experiments. Whereas interestingly, under non-idealized experiments, if you look at the SSP experiments that go past net zero to net negative emissions, SP1-2.6 and SP-3.4 overshoot, those actually don't show this consistent positive asymmetry. In fact, they show something much more that the proportionality actually does still hold. And so there's kind of this weird scenario where the non-idealized experiments are behaving more ideally than the idealized experiments. I should say on these non-idealized experiments, that if you look at the CMIP6 models, that there is any individual model will have some proportionality from of the sort of the proportionality is conserved, with some asymmetry. But that asymmetry is for each model is well explained by this quantity called the zero emissions commitment, or the ZEC, for each model. So they're saying that after you get to net zero, the relationship between global warming and cumulative emissions is defined with proportionality with an asymmetry that's this other metric called ZEC. And ZEC is this other measure of how much warming would occur if CO2 emissions were to abruptly stop. So it's measured by going from a 1% concentration experiment, and at roughly two times CO2, you take the model and allow CO2 to become transient or prognostic with no zero further emissions. What happens is CO2 concentrations decrease, but the temperature remains constant. And so those two, and the reason why is because sinks continue, but the climate sensitivity tends to increase because ocean heat uptake decreases, and the physical climate sensitivity tends to increase in time. So these two effects cancel each other out, giving roughly zero change in warming, but with a range between plus or minus 0.3 C, right? And so TCRE and ZEC are together these key coupled carbon climate sensitivity metrics that are used in the remaining the IPCC remaining carbon budget for climate stabilization. So so what's going on here? Our hypothesis is that that the asymmetry in the 1% concentration is really kind of an artifact. That if you look at the cumulative or the emissions rates that you are required to give you that 1% per year concentration reversal, what you see on the right hand side is that it implies this 50 petagram per year jump in emissions from about plus 30 to about minus 20 petagrams of carbon per year instantaneously, right? And that's a lot to ask of path independence. There'll be path invariant even if you jump instantaneously 50 petagrams of carbon per year, right? Roughly, like currently we're only emitting 10 petagrams of carbon per year, so it's an enormous jump in carbon fluxes that we're asking this path independence to hold over. So what we did here is we wanted to design an experiment that avoided this artifact, what we think is an artifact of this large instantaneous jump in emissions, and design a different way of thinking about these negative emissions experiments. And so what we came up with is idealized climate restoration experiment, which is a continuous to metric transition from positive to negative CO2 emissions. And the simplest way of doing that is think of it as cumulative emissions following a Gaussian, and thus annual emissions following the first derivative of a Gaussian over time. And so we did something where we basically emit 1,000 petagrams of carbon and then negative emit 1,000 petagrams of carbon. Run this through an emissions-driven ESM. And our hypothesis is that warming will follow this TCRE proportionality during the positive emissions phase, and then follow the TCRE proportionality plus this ZEC during the negative emissions phase, because that's what we saw roughly in that less idealized thing. But the key thing is because in the SSP scenarios we have non-CO2 greenhouse gases, you can't actually allow you to estimate the TCRE because the TCRE is a carbon climate only quantity without other greenhouse gases. CESM2 is really ideal for this because it has a very negative ZEC. So because it has this very negative ZEC, it actually allows you to separate this TCRE proportionality from the TCRE plus the ZEC during the negative emissions phase. Okay, so what are the results? So if we do this, this is what the CO2 fluxes in this experiment look like. So again, for first 150 years we do positive emissions, the second 150 years we do negative emissions. Then we ran it out for another 50 years with zero emissions after that. Both the land and ocean sinks follow the emissions, and they flip sign in response to the emissions to become the sinks become sources after emissions become negative emissions. And so you can start to see these kind of roughly, these decadal lags start to happen. Interestingly, the atmospheric growth rate leads emissions precisely because the sinks lag it, right? Because the sinks, the growth rate is emissions minus the sink, and you can sort of work out the trigonometry of why the atmospheric growth rate needs to actually lead the emissions because the sinks lag it. And so that's sort of one interesting result. The climate response follows kind of the expected Gaussian relationship of proportionality to our emissions, right? Because our cumulative emissions are following this Gaussian function, we expect our temperature to also follow this sort of Gaussian function. And it roughly does, but interestingly, it also leads the cumulative emissions for most of this scenario. So temperature is the red line, and you can see it, sort of drops down faster than the negative emission, or the cumulative emissions drop down under negative emissions for most of this scenario, and then it warms a bit at the end. And so there's some interesting stuff going on there. And that's kind of unexpected, right? Why would temperature actually lead the cumulative emissions? And our hypothesis was that the warming would follow this TCRE proportionality on the upslope, and then TCRE plus this ZEC, which for CESM2 cases is negative on the downslope. And it mostly holds, right? That you can see the lines kind of, these two diagonal lines here are the TCRE and the TCRE plus ZEC. And so it's doing this. The interesting thing is that it actually switches from this TCRE line to the TCRE ZEC line before getting to net zero. Right, so this is kind of the surprise. We expected it to follow the black line on the upslope and the blue line on the downslope, and it does that, but it switches actually earlier than we were expecting it to. And so yeah, so what's going on there? Why do you think that's happening? And okay, so that's only for CESM2. It's hard to really say if this is a robust feature of the climate system that we would expect to happen. The ZEC, the ZEC as it appears as a deviation of CCRE would happen before you get to net zero or not. And so we ran this through the FAIR simple climate model through a large ensemble of perturbed parameters in that, the exact same experiment. And we asked how different aspects of the climate response are governed by these two different things, either TCRE or the ZEC. And so the top panel here shows the sort of envelope of temperature trajectories, and then each of these scatter plots shows three different things as a function of either the TCRE or the ZEC. What we see is that kind of as we expect, the peak warming is mainly governed by the TCRE, although as the TCRE plus half of the ZEC actually correlates with an even higher R squared than this TCRE only. The timing of the peak warming, i.e., the relative lag between the peak temperature and the peak cumulative emissions, is actually better governed by ZEC, or is actually very strongly governed by ZEC. And interestingly, it also crosses zero, this line, so that if ZEC is negative, the peak warming actually happens before peak cumulative emissions, i.e. before you get to net zero. And so that's an important update to what we might expect, right? Current climate policy says that once we get to net zero, we expect temperatures to stabilize. And this says, well, if we live on a planet with a negative ZEC, temperatures can actually stabilize slightly before we get to net zero, which is actually good news. The converse of that is also true. If we live on a planet with a large positive ZEC, warming may not happen till well after we get to net zero. But so this says that the ZEC and this relative timing of peak warming and peak cumulative emissions are actually very highly correlated to each other. So this is an important policy relevant point. Interestingly, in this experiment where we then pull out as much CO2 from the atmosphere as we had put into it, this end warming that above the pre-industrial amount is also largely governed by ZEC as well. So just to conclude, CO2 sinks follow emissions under this kind of scenario. Reverse sign becomes sources after emissions reverse with a decade timescale lag. The lag between CO2 fluxes and emissions causes atmospheric CO2 concentrations to actually lead emissions. The TCRE proportionality holds under negative CO2 emissions, subject to an asymmetry that is well quantified by ZEC. So I think what this says is that the result from the 1% per year concentration reversal experiment is largely, that there's this positive asymmetry of the, relative to the TCRE after negative emissions, is largely an artifact of that experimental design, and that huge instantaneous jump in emissions. And if we avoid that, then actually the TCRE proportionality does hold quite well. Lastly, and this is kind of a key point, much of the ZEC appears before reaching net zero, and thus ZEC also governs the timing of peak warming relative to net zero. And so that's an important point for policy, relevant things of saying, because if we get to net zero and climate doesn't stabilize, that's a really important thing that we're going to have to be able to explain. And likewise, if climate stabilizes slightly before, then that's great news. And so thus the ZEC actually works more robustly as a measure of the long-term path dependence and deviation from the TCRE relationship under strong emissions than it does a measure of warming subsequent to reaching net zero, right? So if people tend to define ZEC as, well, how much warming is there going to happen after we get to net zero? But if it actually shows up in the temperature to cumulative emissions relationship before we get to net zero, then it means something different than it's sort of commonly defined as. And so we actually think that there's a better definition of ZEC, which is that it's just simply a measure of the long-term deviation from this TCRE relationship under a high mitigation. Sorry. This should say strong emissions reductions, not strong emissions. I apologize. And then lastly here, some, since this is part of the biogeochemistry working group, I think there's
You're at
this
13
this begs a
minutes.
bunch of interesting questions too, right? One of which I don't think we have a good answer for is why does CESM2 have such a negative ZEC? I think we know why it has such a large TCRE, because it has a high climate sensitivity. I don't think it's as obvious why it has such a negative ZEC. Another point is if the CESM2 ZEC runs are extended longer, do we start to see these kind of weird re-strengthenings like we do in this experiment and in the long-term overshoot experiment? How does land use change into some of this stuff? What aspects of these dynamics are sensitive to parameter and structural things? Differences. And would this be a useful and practical CMIP7 experiment? I think we argue in this paper that it's kind of a more powerful experiment than the 1% per year concentration reversal because it avoids this artifact. So I think it might be useful to consider whether or not this would be a useful starting point for some CMIP7 experiments. And lastly, I just want to end this on how else can we use some emissions-driven CESM experiments to explore some of these climate mitigation scenarios? And then actually lastly, I also just want to plug that we've got a postdoc opening with a link here for anybody interested in postdocs on vegetation dynamics. And so I will end there. Thanks.
All right, thanks. We probably have time for one question.
Charlie, this is Britt. A nice talk. I'm just curious, when you get out to whatever that was, 500 years at the end of the curve, without negative emissions, how much of the land and ocean carbon sinks have returned to the atmosphere? Like, what's the interval under those blue and green curves?
Yeah, I mean, you can see it in the, in the CO2 time series, this sort of pink line here, this concentration, right, is that before you get, like the CO2 actually drops well below the pre-industrial before you've pulled all the CO2 that had been emitted into the atmosphere out of the atmosphere. And the reason for that is that the positive emissions phases had longer time to go into the oceans than the negative emissions pulses. And so, yeah, it takes a while for the ocean to outgas all of the CO2 that had accumulated during the positive emissions phase. And so yeah, the CO2 does gradually go back to the pre-industrial, but approaches it from below rather than from above.
All right, thanks. Our next talk is going to be Thomas Bitnerowicz, who's going to be talking about the temperature response of nitrogen fixation. So this is another remote presentation. So Thomas, if you can unmute yourself and start sharing your screen.
All right, one sec. Can you see my title slide? I don't hear anyone, but I assume that's yes. Hi, I'm Tom Bitnerowicz. I'm a postdoc at UT Austin, and today I'll be talking about some experimental work with nitrogen, the temperature response of nitrogen fixation, and incorporating that into land models. So a quick overview, biological nitrogen fixation is the dominant natural input of new nitrogen into the terrestrial biosphere. Here I'm showing the tree Robinia pseudoacacia, black locust. It's the dominant nitrogen fixing tree in the US. And nitrogen fixing plants, they have root nodules where atmospheric nitrogen is converted to ammonium in exchange for carbon. And there's been multiple approaches to modeling nitrogen fixation in land models. For example, CLM 4.5 used to do this as a function of NPP. Now CLM 5.1, it's more of a process-based approach using the FUN model where N fixation is a function of N demand, plant available carbon, and temperature. And temperature makes sense. For example, a global analysis of nitrogen fixing tree abundance showed that maximum temperature is the best predictor of where nitrogen fixing trees are, followed by temperature in the warmest and wettest quarter as the third and fourth best predictors. And notice that where temperatures are warmer, you have more nitrogen fixing trees. So traditionally, the temperature function that has been in use in models comes from Holton et al. 2008. And this has been the best guess up till some of the data that I'll show you. This has been based on 6 studies, 5 of which were actually from free-living bacteria, not symbiotic nitrogen fixers. But it's been extrapolated to the global scale to model symbiotic nitrogen fixation. So we really wanted to get at the temperature response of symbiotic nitrogen fixation, and we focused on tree fixers for this. As a first step in my PhD, I developed a method to make continuous non-destructive measurements of nitrogen fixation. And that allows us to get at timescales of nitrogen fixation that were not previously accessible by available methods. So we did this for temperature. We did it across 4 species. So 2 of which are tropical, 2 of which are temperate, and then the 2 types of symbioses. So either actinorhizal or rhizobial symbioses. And we did this across a range of growing temperatures spanning 10 degrees Celsius. And here I'm showing each panel has 3 different individuals, and then we fit a function to each column, so for each species across growing temperature, where parameters of the function can acclimate to growing temperature. This analysis was set up this way so that it could be easily plugged into land models. So one of our findings was that optimal temperatures for N fixation are much higher than in the function that has been in use, about 4 to 12 degrees Celsius. And that's largely driven, that range is driven by acclimation to growing temperature, particularly in the tropical species. And we think that our curves are shifted to the right relative to the Holton function, possibly for a couple of reasons. One is that was based on free-living bacteria, not plant bacterial symbioses. And also it had a latitudinal bias to high latitudes. Additionally, I'd like to point out that even temperate fixers grown at cold temperatures had higher optima than the function in use, and then way higher optima occurred in the tropical fixers grown at high temperatures. Those are the 2 top red curves. So now for the modeling part, I'm leading a model intercomparison project across 7 land models. This is ongoing work. So I'll have a couple results to show, preliminary results, but more are coming. And our question is, how do the temperature response of nitrogen fixation and capacity for acclimation affect predictions of N fixation, NPP, and land carbon storage with climate warming? So this kind of relates to this. One of the implications may be testing this projected decline in tropical nitrogen fixation with climate warming, which has been predicted using the Holton function. Here on the right, I'm showing this from the cable model for 3 different levels of CO2. And the question that kind of I'm asking myself now is, how sensitive is this result to the temperature response function of N fixation that is being used? So we're doing a few different approaches with the functions in use. First, we have the original Holton function. Then from our Nature Plants paper, we have a separate temperate and tropical function. Plants kind of been together well by temperate versus tropical origin, not so much by symbiotic type. And this one does not include acclimation. And then we have a third scenario where we do include acclimation, but it only occurs between the range of temperatures we have data for. So in CLM, the way this is implemented is via the FUN model, and there's a temperature-dependent carbon cost of nitrogen fixation. So here I'm plotting up what that cost looks like for the Holton function and our temperate and tropical function that does not include acclimation. Essentially, it flips the function and sets the temperature response function is essentially flipped, and the minimum is set to 6 grams of carbon per gram of nitrogen. We've also started empirically measuring this cost, and our shapes for flipping it actually work pretty well. We've observed minimum costs around 6 to 9 grams of carbon per gram of nitrogen. And then if you get to really low temperatures, that cost rises up to around 150. So just to sum that up, we have 3 approaches for representing nitrogen fixation. And some models, we include a 4th one. For example, Orchidea before this project used a function of NPP scaled by plant and to P ratios. So they have a 4th simulation. And right now we're doing site level simulations for a tropical, a temperate, and a boreal site. And the next step will be global level simulations. We have a historical time period for the simulations from 1850 to 2014, and then 2 future scenarios. One is future warming with fixed CO2 and N deposition, and one is future warming with transient CO2 and N deposition. And we're using EasyMIP GFDL forcing. The future scenarios using SSP 585. So just to give you a flavor of some of the results that we're starting to see, it's all super preliminary. I'll start by just showing what soil temperature in the layer that N fixation responds to looks like. These are monthly means for the temperate and the tropical site. And then, so if we go now to the temperate site, here I'll show how N fixation through time looks like. This is for the transient CO2 and N deposition scenarios. And we're summing right now symbiotic and free living fixation in these plots. Some models separate the two, but Orchidea, for example, does not. So that we can compare apples to apples, they're summed up here. But we did not change how free living fixation is depicted. So on the left, we have the Holton function. On the right, we have the temperate function. In general, with climate change, fixation rates increase at the temperate site, but there's variation in magnitude depending on what model is in use. And then if we look at the difference in fixation between our temperate function and the Holton function, all of this is no acclimation, by the way, we see a consistently higher or lower fixation rate using the temperate function, and that's consistent through time. So that doesn't get affected by climate change. Now at our tropical site, again, on the left, I have the Holton function, and now on the right, I have the tropical function. We generally also see an increase in N fixation through time. The magnitude, again, varies by model. And now if we look at the difference between the tropical and the Holton function, we see that with climate change, we get a divergence happening between the models. And also we see that future scenarios have higher fixation rates for the tropical function than for the Holton function. It'll be really interesting to look at how acclimation affects this, but I have not done that yet. And also what's going on in more models. Right now we have output from 3 of the models and more to come. So I also want to mention that we have NSF funding to continue this experimental work. We got this recently, and this is with colleagues at Columbia University, where I did my PhD. So one of the cool things that's happening with this is a master's student, Vanessa Lau. She's leading work on the temperature response of carbon costs for nitrogen fixation. So that would be directly useful for using the fun model instead of having to flip a temperature response function. And this is also with together with Duncan Mengi and Kevin Griffin. And with that, I'd like to thank my collaborators, both from the modeling side and the empirical side.
Thanks. We've got time for a few questions. And Alea, I guess we've got lots of questions, but if you want to start heading up, getting mic'd up, that'd be great. Anybody have any questions for Thomas? Will.
What happens to carbon?
Carbon's generally increasing with the climate change, but I haven't yet looked at how the divergence between the models. So I guess stay tuned.
And what about in the cold site? I know CLM had bigger results at Bonanza Creek than it did for anywhere else. Did the other models?
Yeah, we added that boreal site to kind of test that. We don't have actually like data right now on boreal nitrogen fixing tree species, but yeah, we're testing that with the temperate function. So we'll still learn a lot from that.
Abby, you had a question?
Oh yeah, I was just wondering if you have plans to try to scale this up to get at sort of global implications of if this changes our view of nitrogen limitation under future climate.
Yeah, so we're gonna, after these site level simulations, a subset of the models, not all of them run globally, will be used for global simulations to test those kind of questions. But yeah, I'm curious, right? Like, will nitrogen supply from fixation increase or decrease with climate change in the tropics? It may be a different direction than previously thought.
Jackie had a question in the chat. She's a great talk. Was Orchidea using an NPP connected fixation? She's commenting that the responses in Orchidea were very strong.
Yeah, I'm not sure how the NPP factors into that right now. Daniel Gall just recently rewrote the formulation for fixation there before it did not have a temperature function. So I'll have to check that, but yeah, thank you for bringing that up. But yeah, that response was much stronger, particularly versus classic from the Canadian ESM. CTSM was kind of in the middle of both of them.
And Josh has a question?
Is the temperature control on nitrogen fixation related to plant side or bacteria side? Because bacteria can adapt incredibly fast, so over long-term climate change, they might change their ability, their optimal temperature. The trees, not so much. They don't have as much time to adapt. Would that potentially change things, or do you know if there's potential for that or not?
Yeah, I guess the only experimental side of adaptation we have on that is looking across species. So for example, all of these plants were grown with field collected bacteria. So the tropical species actually grown under cold temperatures and even medium temperatures had pretty similar temperature response curves to the temperate species. Of course, that's not adaptation within a species or within bacterial lineage. But then acclimation was very different. But there has been some work on free living fixation temperature response curves that came out a few years ago, and they were seeing quite a bit of adaptation within a certain lineage of bacteria that associated with lichens. So I think there's quite a possibility for that. We just haven't really observed it yet.
Thanks again, Thomas. Our next talk is going to be from Alea Kaushik, who's talking about plant drought responses.
All right, is the mic working? Cool. Should I start or you make it? There we go. Okay, cool. All right, thanks. It's been a really fun couple days. It's been a while since I've been to a land model working group meeting, so it's been super fun. So I'm gonna switch gears a little bit and spend some time talking about how we've used isotopes to study plant drought stress responses in North American ecosystems. I just want to shout out to, there's a whole bunch of collaborators on this from the modeling side as well as from the data collection side in GML, so just a big shout out to everybody. And also funding from the NOAA MAP program. Okay, so the motivation for this work came from the fact that so the interaction between plants and environmental stress can actually mediate how that drought stress response is manifest in different ecosystems. And this figure here shows that you can, oops. Okay, this figure shows changes in the model conductance as a function of vapor pressure deficit, where VPD is essentially a measure of stress. And as you're increasing vapor pressure deficit or increasing stress, that's the model conductance drops off. But depending on whether you're a forest or a grassland or something in between, the rate of drop off is different. But at the same time, Whether you're a forest or a grassland or something in between, you can still maintain a certain level of gross ecosystem productivity. And this is all down to this plant stomatal response, which you've heard mentioned several times this week. And that is the focus of our study, is this stomatal interaction between plants and the environment. And the simulations I'm going to show you with the model that we've been running, we also are looking at this impact of higher atmospheric CO2 on the simulations, and that also plays a role in this stomatal closure story. So I'm going to be spending the talk talking about the atmospheric delta C13 tracer, so delta C13 of CO2 in particular. The theoretical basis for this is that plants prefer carbon-12 or the lighter carbon for photosynthesis, but when they're stressed out, they don't have a choice, so they take whatever they can, and so that leads to less discrimination, which leads to relationships like this, where you see a different isotopic discrimination signature as a function of net carbon uptake. So this was a paper that was done in 2018 where they looked at a bunch of inversion model results, but they showed this nice anti-correlative relationship between the isotopic discrimination signature and net carbon uptake. And so we're kind of leveraging that story to use C13 to trace drought stress. So again, the reason for this is because as the CO2 passes from the atmosphere through various resistances or conductances, depending on how you like to think of them, into the chloroplast where it gets fixed, each of these stages is associated with a different isotopic signature or a fractionation signature, and then you can construct an equation like this and then calculate, as a result of all of these processes put together, what your final photosynthetic fractionation signal is going to be. And in SIB4, which is the model that I'll get into in the next slide and tell you a little bit more about, we modeled the stomatal conductance as a function of Ballberry. And so that's primarily how the stress response in the plants is connected to the stomatal conductance factor. So this was put in a SIB 2.5. We've developed it and also added this additional photorespiration term. And then just to give you a little bit of background about the model, SIB shares a lot of common ancestry with CLM, so I wouldn't be surprised if I looked at the parameter tables that we use similar parameters as well. It's simplified, as the name suggests, compared to CLM, and my focus has been on developing the land surface part of this model, and particularly the carbon cycle part of it. So I mentioned we've got fractionation during photosynthesis. We also put in a parallel pool structure. So now the CO2 molecule, as it passes through the different carbon pools, we also have a C13 CO2 molecule that passes through all the different C13 pools. And then just some technical details about the model. We spin it up in pre-industrial and then run it forward for 172 years. And we do vary the boundary conditions, as I mentioned in the beginning, both the atmospheric delta C13 based on a compiled NOAA Instar record, as well as the CO2 mixed layer concentration over time. Okay, so what does this look like? So I'm showing you results here for an evergreen needleleaf site in Wyoming. And I've just pulled the summer months for the years between 2000 and 2020. So each of these points is an average over that summer growing season period. And I've colored the dots here as a function of DSCI, which is the Drought Severity Coverage Index. It's a composite drought monitor that comes from the UNL Drought Monitor. So it's a composite index that takes into account the severity of all the different categories and bins it as one number. But the main take home here is that the darker colors, so DSCI greater than 300 to 400, are more severe drought conditions, and then the yellows are less severe drought conditions, and you can see that separated as a function of vapor pressure deficit. And the nice thing here is that we're seeing SIB4 kind of out of the box is doing what we expect in terms of the isotopic fractionation signature being different depending on how severe the drought is. So we can also look at different evergreen needleleaf forests at different locations in the US. So the black squares are Howland Forest, the red circles are the Gliese site that I just showed you, and then the green triangles are the Metolius site up in Oregon. So what the point I'm making here is that across different sites in the US, you also see different magnitudes of this enrichment, and at some sites like Howland, you actually don't have that many drought events for DSCI greater than 200, whereas at Metolius and Gliese, you have lots of drought events, but then the magnitude of the enrichment differs from site to site, which is all climate dependent, depending on where this evergreen forest is situated. So we can also look at it in anomaly space. So each of these plots, I'm plotting the anomaly in the fractionation against the anomaly in NEE, which is the net carbon uptake. And then the colors are all representing drought categories, where the bluer colors are less severe drought, red is more severe drought. So we do see, as we expect, that under more severe drought conditions, we're seeing both positive NEE anomalies, which is carbon being released as opposed to being taken up, and then also positive delta C13 anomalies. So again, the model is behaving as we expect, which is good. We're also not seeing changes for C4 plants, also as expected, because they're more hot adapted, but also they don't have as many of the stomatal steps involved in C4 versus the C3 pathway, which I won't get into. And then forests, this is kind of interesting. For shrublands, you kind of see this like gradual departure as you go to more severe drought categories. For forests, the drought category doesn't really make a difference until you hit the most extreme drought class, and then that's when we start seeing the anomalies jump. If we look at the spatial distribution of these across the US, most of the reason for the color scale difference is because of the proportion of C3 versus C4 plants. So C3 and C4 plants have different isotopic signatures. C4s are more in the -4 range, and then C3 is more -18. And then the subtle coloring of the oranges and reds and yellows are all climate stress, essentially. And then the high granular variability in kind of the central US is also driven by this mixed grid pixels, as well as different climate impacts. So I showed you that graph in the beginning of the isotopic discrimination as a function of NEE, and how the Peters et al. Paper found this nice relationship for net carbon uptake. And so we did the same kind of thing, but we tried to break it down a little bit more into plant functional types. And so what I'm showing here is that if we do it for evergreen needle leaf forests in the US, we are seeing this really nice anti-correlative relationship that we were hoping to see, but not so much for the C3 grasslands. And so this speaks to, obviously, the plant physiological differences between these functional types, but it's also a cautionary note that when we're doing this kind of regional modeling across different regions that include multiple plant functional types, we need to be careful as to how we interpret them. Okay, so I'm going to spend the last few minutes talking about how we're using our atmospheric data at GML. So we have a really rich record of flask data across the US for CO2, delta 13C in CO2, and a whole bunch of other trace gases. But what we did was we're trying to use that atmospheric delta C13 signal from the observation side and then modeling it as well as a function of these tracers, which I'll get into in a minute, and then just trying to see if that tells us something about what that model data mismatch tells us about what's wrong in our models and what we could improve. So I'm not going to get into the details of all of these different terms, but this is essentially how you would construct a C13 budget. Some of these terms, like the fossil delta C13 signature, the net ocean, to some extent the ocean disequilibrium as well, they're reasonably well known. Quite a lot of the variability comes from the land terms, though. And so if we look at this kind of forward modeling scenario where you take each of those tracers and then you transport them forward through an atmospheric transport model, and in our case we're using TM5, and then you can compare the time series that you get from the model, which is in red, to the observations, which are in black. This is the SGP site, which is a site for which we have a really nice long record. And you can see that there is two things. One is that we're offset from the one-to-one line, but there's also a trend in the model which is not there in the observations. And we think that this is due to this land disequilibrium term. And I won't dwell on it too much in this talk, but we are, for a separate project, developing a different modeling scenario for the land disequilibrium where we've adjusted that based on observed carbon residence time. So if anyone's interested in this topic, we can chat about it offline or afterwards. But adjusting that carbon residence time in SIB4, because we know SIB4 carbon pools are too young, essentially. So if we adjust that based on observations and scale them, then we see a slightly better match with the trend, although we're still offset from the one-to-one line. So, okay, coming back to the fact that we're going to ignore the fact that we don't get the trend, but then we can detrend it and look at the results in anomaly space. And what we're seeing is that we actually get the phasing and timing of the seasonal cycles relatively well, but we're missing the magnitude. So we're not seeing the dynamic range, and we're not capturing the highs and the lows, which is why we're much more different angle out the one-to-one line. We can also look at atmospheric CO2. And so if we do the same type of analysis where here I'm showing you the CO2 absolute values, we do a much better job matching the absolute CO2 values, which is hopefully to be expected and a good thing. And it's actually even better if we look at some of our background sites. This is a continental site, and so there's some more noise around the one-to-one line. But if you look at a place like Mauna Loa or South Pole, this is a really tight relationship, both for the absolute values as well as for the anomaly values. But at this SGP site, what we're seeing is that even in CO2 space, there are some really high CO2 values that we're still missing in our forward modeling scenario. So that hints that there's something in our model that we're missing in terms of mortality or stress or something that we should be causing the model values to be higher than they actually are. So finally, we can bring it back to looking at a drought index, which is what I had mentioned. I'm trying to kind of not benchmark exactly, but use that as a way to parse our atmospheric data. So this is, again, the DSCI drought severity coverage index, but for the SGP site. And then I went ahead and binned it in categories of 100. And what we're seeing here, again, is that the dynamic range, which is so the size of the red bars, is much less than the observation. So kind of backing up what I showed you in the previous slide, but that our model is basically missing the dynamic range for the anomalies. And then except for the most severe drought category, we're kind of about neutral, both in observation space as well as model space. And so the model does kind of track the trend in the observations fairly well. We're just not capturing the dynamic range. And I'm done. So just wanted to throw out there that we're using atmospheric CO2 as a tracer, and I'd love for this to become more of a CLM collaboration at some point in the future. I think that'd be really cool. And that we have a ways to go in terms of figuring out, we're experimenting with different stress setups, and I didn't get into how we even model stress, but we can talk about that offline again. So I'm happy to take questions. Thank you.
Great talk, thanks. I was curious how much of the response you think, since high VPDs are often high leaf temperatures, I'm wondering how much of the role of leaf temperature on the photorespiration fractionation plays a role in your fractionation relationship?
Yeah, so in SIB, this is a good time to get into the stress aspect of it. We actually model stress as a function of high temperature and moisture stress as well as humidity stress, so we can separate out these three things. I'm in the process of breaking this down, but I don't have an answer for you today.
What would that plot look like if you showed it for annual means or deseasonalized values? How do you capture the annual variability?
I'll make that plot and get back to you. I don't know. We were interested in actually seeing if we could capture the subseasonal variability, so that's why we did it in this space. But on an annual mean basis, I think it would look something like that plot up there, because those are annual means. But this site, so the slight complication with using NOAA data is that the site is not one PFT, right? It's representative of a much larger area. So we kind of have to do an aerial deconvolution of which plant types we're representing, and then maybe use something like that and do a weighting of all the different plant types, and then kind of figure out annual means from that point.
What is the site?
This is SGP. It's at ARM, the ARM lab.
Can I? Actually,
yeah.
Go ahead. Someone else had a question? No. Okay, do you know, I'm just trying to understand mechanism, why plants prefer C12?
It's just energetically more favorable to use the lighter molecules. I think that's my really simple biological explanation. I'm sure there's a more detailed energetics relationship, but I think that's basically.
It's genetics. Right? It would diffuse at a different rate through the stomata also.
Yeah,
it would just be what?
Just diffuse at a different rate also.
Yeah, and the enzyme is smaller mass, so it's faster turnover.
Is there a question back somewhere?
I just have a random marine thought. Do phytoplankton, when they're under stress, also have this isotope fractionation difference?
So my understanding for phytoplankton is that they take up the dissolved CO2, and there isn't so much of a, because there's so much dissolved CO2, it's not like that becomes.
Yeah, but they leave behind del-13C.
Oh, there's definitely fractionation associated with primary production. I was going to say photosynthesis in the ocean, but I don't think that's the right term. But I haven't looked at that. I know, so part of our budget is the ocean exchange, and there's other people working on that, so I'll ask them to get back to you.
All right, thank you. Manoj Pari will be our next speaker. He's also here. And he's going to be talking about the impact of aerosols on ecosystem productivity in India.
You guys hear me? Okay, great. Thank you for having me here. Myself Manoj, and I'm from India. I'm a graduate student over there, and currently I'm a visitor here at NCAR. Thanks to Danica and Professor Tyagi for that. Well, today I'll be discussing about the effect of aerosols over net primary productivity across different agroclimatic regions over India. So for this, as you all know that like carbon has both positive and negative effects on the ecosystem as well as in the climate. But then there are other factors that determine the intensity of these effects. And one such effect that we'll be discussing about is like the radiative transfer effect. Well, they have a possibility of transferring because of the diffuse radiation, they either promote the carbon flex or like the demode based upon the CO2 fertilization in the ecosystem. But then they leave us with a one particular question that like at what degree these effects of aerosols on the primary productivity is inverse, like whether they tip this effect in a positive manner or in a negative manner. So in order to understand this question, so we framed this study with a simple remote sensing process-based model called CASA, which is Carnegie Ames Stanford approach model. And we used Moody's aerosol products in order to compare this relation. So to find the radiative effect, we used SB-DART model, and we coupled it with in order to find the spatial sensitivity across different regions of India. So to understand this, we distinguishedly classified India into 15 climatic divisions based upon the climatic conditions and the vegetational background. Well, the plot here you are seeing is like the aerosol trend for the period of 20 years, where you can see there is a distinct trend of positive aerosol accumulation over the eastern front, which is mostly dominated by the agro regions. That's usually like this intensity of aerosols is usually maintained by the seasonal cropping pattern and the biomass burning that is being taking place over the region. On the other hand, if you look at the primary productivity, you can see a strong positive trend over the period, especially on the central zone and the northern zone. But then if you just take like the western front and the northeastern front, you have a gradual decrease in the net primary productivity, and that's where you have most of the forest-based ecosystems present. So you have evergreen broadleaf forest and evergreen deciduous forest over these two regions, and they account a significant loss of about 5% of total loss of net primary productivity for the whole period. If you look at a temporal extent, where you can see we compared the CASA model with the trendy ensemble and with the Moody's product, where we could able to see there is a harmony in between these two products, where you have a gradual increase in the trend. But then if you look at the decadal shift, at the decadal level, you have a steady phase at the second decade where the trend seems to be a little poised down because of the loss of productivity in the forest-based ecosystem. But here the gray shaded regions represents the AOD period, when the AOD is like lesser than the actual threshold for the overall average scale. But then the red phase indicates the average aerosols are like higher than the average threshold. And that's usually, it's synchronized with the detrended anomalies where the maximum productivity has been observed in the previous decade. But later on, if you just go with the later decade where you have higher AOD chances, where you have loss of NPP in those regions. So this table over here, it represents the decadal and the seasonal variability in comparison with CASA and other models, where you can see like CASA has able to harmoniously track the productivity across decadal and seasonal scale in terms of trendy. But then if you look CLM particularly, it almost like underrepresented at CLM compared to the other models. Particularly if you look at the monsoon, where the shift has been transferred towards monsoon rather than at the post-monsoon if you are comparing the other model. On a spatial extent, if you look at the aerosol variability across different regions, where you can see you have higher seasonal variability over the regions that is being plotted in orange. They usually represent the region that have agro-based ecosystems on the region. But then if you look at the green phase over here, so this is mostly the region where you have like higher forest-based ecosystem, where you have the poised aerosol trend. On the other hand, if you look at the NPP trend, this represents the whole like seasonal variability of NPP. Again, you can see a higher variability of NPP over there in the agro ecosystems rather than at the forest-based ecosystems. But then what we did is like we segregated the years or like the period when you have lower AOD, where you can see the green lines represents that's the productivity when the aerosols over the particular region has been lesser, lesser than the actual threshold, and that's when you have AOD has been like, the NPP is like increased over these regions, especially on the forest-based ecosystem rather than in the agro ecosystems. But then when the AOD was like higher than the actual threshold over the region, you could see the NPP has been decreased irrespective of the ecosystems. If you compare the agro ecosystems as well as in the forest-based ecosystem, NPP seems to be drastically reduced at different level. So that's when we used like the radiative transfer model in order to understand how this shift has been, the sensitivity has been playing between AOD and NPP. So we figured it out that like NPP has been having like inversely proportional to AOD, and it is like having higher sensitivity at different zones at like different bins. But then if you look particularly on the forest-based ecosystem, where you have maximum AOD at the maximum productivity was at like 0.38 when the AOD was like 0.38, but then the growth of NPP was persisted when it reached 0.5 and above. On the other hand, if you look at the agro ecosystems, where the growth of NPP was restricted when it increased 0.6 and above, but the maximum growth of NPP was observed when the aerosol hit like 0.5. So on an overall scale, we understood like when the aerosol of the particular region, it increases to 42% of the overall region, it stops the NPP productivity at a significant level. Whereas if the AOD is like lesser than 14% of the overall region threshold, it promotes NPP at a significant rate. So this sensitivity helps us to understand, to calculate the sensitivity between different regions. Based upon this one, the maximum negative effects has been found on the Western Plateau and the Eastern Plateau front, where the minimum enhancement was being found at the Western Plateau and the Eastern Plateau, whereas the maximum enhancement of productivity because of the sensitivity of AOD has been observed in the Eastern Himalayas and in the Eastern Coastal Plains that we saw, that was considered to be dominant of forest-based ecosystem. So to understand this analysis, we spatially found the regions that has been sensitive to AOD and that has been marked on a red box with a stipulated point. When we plot on a normal scale where you have a poised level of NPP over the region, but then if you just look at those particular points where the red line indicates, that's when you have higher NPP productivity over the post-monsoon season when AOD is like lesser. But then if you consider when there is like actually higher AOD in the monsoon season, the NPP trend seems to be reduced in this region. So this region is like the Eastern Coastal Plain where you have the mixed canopy layers. It includes that like both evergreen broadleaf forest and deciduous forest. So we extrapolated this analysis to few other heterogenetic background of regions, but this region is like represents the region that has active agricultural background, and this region represents both have multiple layer canopy system. And you can see when the AOD is like having higher, it almost like induces the NPP rather than at the when AOD is like lesser than the optimal threshold. But then if you look at the other with the multiple layer canopy region, it doesn't show much variability over this over the period. So based upon this analysis, we came to understand that like NPP is AOD is like playing is like regionally syncline, and it is like having heterogeneous background depending upon the regional aerosol load and the vegetational background. So to summarize all the study, we found that like India is having a gradual increase in the productivity, but then if we note at a decadal scale, it seems to be like the later decade is on a dip. But if we look at a sensitive level, where based upon the canopy architecture, the forest-based ecosystem has plays a major role than in the agro ecosystems. And in case of some drawbacks we had as well, so this is like this is like a mono scenario study, but then if we compare it with like multiple scenario study, we could able to identify more sensitive regions across India. And the other thing is like we since it's like we spatially averaged all the pixels, so that we fail to capture a phenological difference between like each regions. And with that, concluding. Thank you.
Thanks. We have time for a few questions. So I have a question. I feel like in some of the observational-based studies, they actually show that there's a bigger effect of diffuse light induced from aerosol in crops as opposed to forests. Like, do you have any sort of observational targets that you can compare here to see if just the system behaves differently in the subtropics or given the types of crops that are being used?
So that's one of the major drawback of the study, because like we don't have India is not well sophisticated with the flux networks or any other network, so we couldn't able to like validate this study based upon at the ground level. But otherwise, that's why we use the remote sensing products in order to do the analysis.
Thanks, that was really neat. The next talk will be Keith Lindsay, who's also here in person, and he's going to be talking about fast spin up.
Thank you.
Should I be doing the slides or? Thank you. So my name is Keith Lindsay, and I'm going to be this is very much I'm going to give an update on some fast spin-up techniques for different components of an Earth system model. This is very much a work in progress, so this is not a final product that's ready to be used by others yet. That's the goal, to be there. This is work that I'm doing jointly with Sam Levis and Will Weeder. Broadly speaking, what the statement of the spin-up problem is to generate tracers or pool distributions that are in balance with respect to some time varying forcing. There are many different applications for this. One is to initialize transient experiments, analyze dynamics or properties of spun-up tracers being spun up. If you have nonlinear dynamics, analyzing the dynamic of those nonlinear dynamics when you're not spun up might yield different analysis results than when they are spun up. You want to compare your tracers or pools to observations. You might want to do optimization of parameters to reduce model bias. And that has shown up in a variety of talks that have happened in the LMWG earlier this week. This requires the ability to spin up repeatedly. So you want something that's fast and efficient, and that has shown up in a number of talks. Doing a brute force is prohibitively expensive, particularly for ocean models, where running for 2,000 years might take you 40 wall clock days, and that's not something you can do repeatedly. So I'm a mathematician by training, so I'm translating this into a mathematical framework and then use tools of mathematics to attack this. So the notation that I'm introducing is that C of t is the tracer or pool state of the model. In the ocean, that's tracer concentrations, or this might be pools in the land model. This is a vector in some high dimensional space. So with our POP ocean model for one tracer, we're talking about 4 million degrees of freedom. In our MOB model, we're about 10 to the 7th. And if you're looking at a climate resolution version of CLM with the soil model, we're talking also about 10 million or so variables. So we're in a high dimensional space that we're applying the mathematical tools to. If you sort of break down what does represent the forward model into just to wrap everything up into one function that maps an initial state to a state at time t, and I'm labeling that as phi. So that's the result of integrating all tendencies in the model forward in time from an initial state to time t. The spin-up problem is to find a special initial condition, C star, such that when you initialize the model with C star and run it with period capital T, you get back to where you are. So this is the end state is the beginning state in this big high dimensional space. And T here is the period of forcing of interest. So this might be 10 or 20 years that captures interannual variability, or if you've got something, you might do a shorter if you're just looking at some sort of synthetic annual forcing. But typically with climate applications spinning up for initializing coupled models, this might be 10 to 20 years. Now to apply the tools of mathematics, I'm going to take this equation of, does my cursor show up? Yes. We're going to take this and then rewrite this as phi of ct minus c and set as a function g, and we want that to be 0. And now we're trying to find the 0 of a function, and that is where math comes into play. We're going to use Newton's method to find the 0 of that function. Newton's method is an iterative method that you might have learned about in calculus class for one-dimensional variables. This is just like that, except that it's in a million-dimensional space instead of one dimension. What Newton's method does is it generates a sequence of iterates that converge to the solution for a system of equations. And the way that Newton's method is derived is you take your function that you're trying to find the 0 of, g, you're evaluating it, you've got a current iterate, c sub k, and you write the value of the function of your next iterate, g of k plus 1, do a Taylor series expansion about your previous existing iterate. So g of ck plus 1 equals g of ck plus a partial derivative times the difference here. This is a Taylor series expansion. And then we drop all the nonlinear terms. So we're doing a linearization of this big function with respect to your difference between your iterates. We drop all the higher order terms and solve for ck plus 1. What ck plus 1 with that linearization gives you a 0. And if you rearrange terms, then you end up getting you get this equation right here. So the equation for this Newton increment is what you're adding to your current iterate to get to the next iterate. And that solves a linear system of equations. So there's a derivative times an increment is equal to a right-hand side. That is the linear system of equations that you are solving to get the Newton increment. And if you solve that exactly, then Newton's method converges very quickly to the global solution, a global solution, I should say. However, that's easier said than done. Computing that increment is solving this system of equations, but I mentioned this is we are in a million-dimensional space or 10 million-dimensional space, and this linear system of equations tends to be dense. So it's not feasible to actually compute that matrix of partial derivatives, much less store it. If you've got a 10 million by 10 million matrix, we don't have enough disk space even on our supercomputers to store that. So that's not you don't solve this system of linear equations directly. You need to find a way to approximate the linear system of equations. And so what I'm using in this technique is another iterative method to solve for the Newton increment. It's an iterative method inside an iterative method, which is we're using a Krylov method, which is a particular class of iterative methods for systems of linear equations that's well suited for this scenario. I'm not going to go into the details of Krylov methods, but the key feature is that you end up computing a matrix vector multiply in each iteration of the Krylov method. And in order to compute this in this scenario, We don't actually have this matrix, so we can't really compute a matrix vector multiply. But what we do is we approximate it with a finite difference by computing the g function with a perturbed initial state minus an unperturbed g divided by the size of an increment. And the key thing is that evaluating this right-hand side is doing a forward model run of length t, because that's evaluating this function g, which is end state minus beginning state. So if you start thinking globally, hey, what's going on? We've got this outer iterative method, Newton's method. Inside that is another iterative method, the Krylov method. And each step of that inner loop is doing a forward model run of time t. In order for the Krylov method to actually converge efficiently, we need to apply a technique called preconditioning to that system of linear equations where you are approximating the inverse of that matrix. And that is where a lot of the art of doing these types of techniques comes into play, is constructing a preconditioner that is a good approximation but is also feasible to compute. And I'm not going to go into the details of that, but suffice it to say that's where a lot of the work comes into play. I've given some talks on this before about applying this to ocean tracers. What's different about this talk is that we're now applying this to soil pools and CLM. Some issues that end up coming into the challenges and issues that end up arising are that Newton increment can lead to non-physical values. So you might get a negative tracer concentration or a negative carbon pool in the land model. And there are some ways that you can scale down the increment to ensure that you get physical values, that you don't shoot off your increments into a non-physical regime. Another challenge is that Newton's method is doing this linearization of your function over the time scale of big capital T. But if your model has strong nonlinearities on shorter time scales, the linearization, they may not play friendly with the linearization of Newton's method on the time scales that you're applying it to. And so one of the techniques that we're applying to these is apply Newton's method to what I'm calling shadow tracers. So basically cut off some of the feedbacks that lead to, between some pools in your system, cut off the feedbacks that lead to those fast nonlinearities. So for example, in the soil pools, cut off the feedback between the soil decomposition and GPP, and then just spin up your soil pools with fixed GPP, with fixed inputs into your soil pool, and then apply the Newton's method to that, then copy them back to the real pool, let your fast pools adjust, and then iterate again. So this is another iteration on top of all these nested iterations. So it gets kind of complicated to describe all of this in one place with all of these nested iterations. There's been some talk about applying this to CLM for many years, actually. When I've talked about this in the Ocean Model Working Group, some folks in the land group have asked me, I've got some emails back from 2015 where people have asked me, oh, is this possible to apply this to CLM? And being young and naive, I thought, well, sure, all the math would work fine. Well, at least one of those statements is true about being young and naive. And so in more recent time, there's been talk about doing this for many years, but actually the work to do it is actually more transpired in the last year or so, collaborating with Will and with Sam. And some of the fundamental questions, so the background is that there is a current approach for doing spin up in the land model of accelerated decomposition that many of you in this room are probably familiar with, to spin up the below ground pools. And one open question is, if we get Newton-Krylov working for the land model, is it faster than accelerated decomposition? And this would be relevant for doing high-res simulations where AD becomes expensive, or for things like the PPE that we heard about yesterday, or other experiments where people are trying to do multiple spin-ups. Another issue with AD is that it's not compatible with the soil microbial model mimics because of the nonlinearities between the microbial pools and the soil pools, break assumptions that are present in the AD. And so can Newton-Krylov fill the gap on that? Thank you. We ended up with a very simple plan, very naive plan, get NK working with a single column without mimics, get it working in the global model, then extend to mimics. as I said, this is naive. Easier said than done. I'm going to skip some of this description about the iterative nature of how this project has proceeded. And sometimes the iterations in solving problems has been easy to do, like just adding more history variables to the land model. Sometimes it requires more sophisticated knowledge of the underpinning dynamics in the land model. And this is where the collaboration between myself as a mathematician and Will and Sam as their experts in CLM comes into play. We recently got this working with a single boreal column forest. And this is now, the horizontal axis is Newton iterations. And this is a penalty function written in log space where we're getting exponential convergence. So this is spinning up that boreal forest column in 300 model years instead of what would take thousands of years to do brute force. So we've tried to extend this to more complicated situations. And so we're now applying this. This is an example of applying it to a global course simulation. And this is my favorite column, column 108 in a course resolution model where we get exponential convergence, even converging even faster than that boreal forest over 10 iterations, converging very, very quickly. The next column over, things are not quite, that's not my favorite column. We suddenly get a spike in our residual in 1 Newton iteration, and then in subsequent Newton iterations, things improve better than they were before. So the dynamics of the solver applied to the different columns is pretty complicated. And then one of my least favorite columns is column 113, where I just scratch my head and say, what's going on? And I need to talk to Will and Sam more about where we get something like a period 3 oscillation going on. So this is a work in progress of, and this is now a map of any E after 0 iterations in 10 Newton iterations on a sort of a logarithmic scale. So you can see in many places the solver is really getting towards convergence. We're going from the yellows into the deeper colors, but in some points it's getting worse. So there's a lot going on, and we need to figure out what's going on with the preconditioner of how to improve things. And so this, I said, this is a work in progress. What's going on with the programmatic runs? Why does it require so many Newton iterations? When I showed that single column, it was taking 50 Newton iterations. I'm used to seeing about 3 Newton iterations for convergence in the ocean model. So it's actually going a lot slower than I would hope it would go. And there's some other outstanding questions that we're working on, and then outstanding questions like, can we even extend this to something like the Fates model? So I'll close there.
Really cool. We are sort of out of time, so maybe if folks can talk to Keith with questions.
We have a discussion period at the end.
Yeah, we do have a discussion period at the end, and hopefully Keith will be around through lunch. Folks can talk to him. And we will transition now to Marius Lambert, who is simulating terrestrial DOC production and export within the CTSM.
Yeah, following this talk, we'll have a period of discussion before lunch.
All right, Marius, can you test out your mic? We can't hear you.
You're muted, so. You unmute, you need to unmute.
Now it's good?
Good now. Can you go into full presenter mode or full screen?
I'm not in full screen now.
No, we see your just regular PowerPoint window.
It was better before.
Yeah.
Now we just see a black square.
We have to go back.
I don't know. This is not enough.
Do you want to?
Nick says to use screen share rather than window share.
But if we have to go back to this, it will work.
Now?
Yes, that looks great. Great. Go ahead.
Okay, thanks. So I recently finished my PhD at the University of Oslo, and I was working with Fates Hydro. And in the last couple of months, like 4 months, more or less, I've been working with trying to produce DOC in the CTSM model and export this to Mozart and transport it in the river network. And so first, a little bit of theory. What is dissolved organic matter? It's defined as the organic matter fraction in solution that passes through a small diameter filter. It's often quantified as its carbon content, which is called dissolved organic carbon. But dissolved organic matter also encompasses dissolved organic nitrogen and other compounds. And the lateral flux of carbon that goes into the rivers is a huge amount of carbon. So the decomposition model of CLM is represented here in this picture that I took from the documentation, where you can see different carbon pools. First starting with the coarse wood, and then the litter pools, and then the soil pools. And you see that there's a vertical vertical pools as well. So each soil layer has one pool, and then you can have carbon transferred from the less decomposed carbon pools, which are on top, to the more decomposed pools on the bottom. And so in each pool, carbon has some turnover time, which is in years here. And so when carbon is transferred from one pool to the other, there is a small flux, which is the respiration, the fraction of respiration. And so our first idea was to add a small term, which will be the DOC production. So every time carbon is transferred from one pool to the other, we have respiration and DOC production. And this is the equation here. And so we added this term of production of DOC. And we started by putting some just random parameter to test if the model will work. So we have everything that's in the produced at the surface. We put this in a surface DOC pool, and everything that's produced below the surface we put in the subsurface DOC pool. And then here are some maps of preliminary results showing how much carbon is produced in the subsurface and at the surface. We see that there is much more produced in all the soil layers than just the surface layer, and it's also a different distribution. And yeah, it's much smaller than the respiration. That's because of the parameters that are much smaller as well. Here we can see different soil layers from soil layer 0 to soil layer 14. And obviously there's more DOC produced in the top layers because it's proportional to the decomposition of carbon. And so it depends on temperature, water, and so on. And so then when we have these two DOC pools, surface and subsurface, each of them will be either sent to Mozart or accumulated in CTSM, depending on how much water is sent to Mozart in the surface and in the subsurface. So I put like a random parameter for the moment, which is 0.3 grams per liter. I don't want more than this concentration of 0.3 grams per liter to go to Mozart. And so if there is excess DOC, I will keep in CTSM. So here we see that there is much more subsurface water runoff than surface water runoff than subsurface water runoff. There is much more DOC that is accumulated in CTSM in the subsurface because there is not enough water to transport this DOC produced there. But there is much more
so there is very little surface DOC accumulating in CTSM. Almost everything is sent to Mozart. So Mozart is one of the river models in CTSM. There has been another presentation with Mizerut, which is more like water, like basins with different shapes, polygonal shapes, I think. And here it's more like Gritzel based, I think. So it's the Mozart model is divided in 3 areas. And so the surface water will go to the hill slope part. And the hill slope water will then go to the subnetwork part of the model, where the subsurface water will go directly to the subnetwork part. And so subnetwork part will accumulate both what's coming from the hill slope and the subsurface, and everything goes to the main channels, which link together the different grid cells of the model. And so what I do, I put the surface DOC with the surface water into the hill slope, and the subsurface DOC straight into the subnetwork routing part with the subsurface water. And so here I showed the example of how I will make the DOC move along with the water. I showed the example for the main channel, but it's more or less it's the same concept for the hill slope and the subnetwork part. So what we do is that we have the concentration in each of the parts of the model. And so while we're looping over each of those parts, we will have the concentration is updated at every time step. And so I will compute how much DOC, the mass of DOC already in each of those parts. And I will add the mass coming in, remove the mass that's going out, and divide by the total amount of water in this part of the model. And so, yeah, these are the inputs. So it's the surface DOC, subsurface DOC is the same as I showed in Mozart. It's just different units. And yeah, liquid water below, it's just different units as well. But it's the same that what's going out of CTSM. And so here we see the concentration. I changed the scale a little bit so that we can see something, but I check all the values are between 0 and 0.3 grams per liter. So 0.3 kilograms per cubic meter. And then here I showed storage of DOC in kilograms compared to the storage of liquid water in the model, and the river discharge over land of DOC and the river discharge to the ocean of DOC. And so obviously I've been working only a couple of months on this, so I'm not an expert at all, and this is just preliminarily work. But there are many things to do. And right now I'm trying to verify that the DOC mass balance is around 0 when I integrate a simulation over time, because I think there is more DOC coming out than that's coming into the model, weirdly. And that may be because of the water in Mozart, that sometimes it's like the water storage is below 0. And so there are some problems when the water goes from positive to negative values in the different pools of the model, and then when it goes back to positive values. So I have to double check this. But then there are many things to do ahead, like compare these two observations that we have around and in Norway. And then there are many nice things that we can do in addition to this. Firstly, probably improve the DOC production parameters that I showed, which are just broad estimations, and maybe even change the equation. So have an independent equation for DOC production that is not part of this decomposition equation. And then have some differentiation for recalcitrant and labile DOC pools, add DON as a tracer. Because right now I added this whole, the whole code is an array that is transported DOC, but it will be very easy to just add DON because I do it the same way liquid and ice are transported into the model. It's like just a tracer, so it will be really easy to add DON once we have it as an output of CTSM. And then adding DOM going back to land, but then, yeah, I right now I don't do anything with the DOC that's going into the ocean, and I don't do anything with the DOC that's accumulating in the pools over land. So that's some stuff I have to do as well. So thank you for listening, and I hope this will trigger some interesting discussions.
Thank you. That's really cool. This is one of the things that we've talked about for the BGC-WG over the years, is trying to, fully integrate the land and oceans, not just via their imprint on the atmosphere, but also through this, sort of dissolved organic matter and riverine transport between the land and the oceans. It's really neat. Does anybody have any questions in the room? I see there's one in the chat from Katie Rochi. Interesting work in your modeling scheme. Is there any opportunity for DOC lost via decomposition in upper soil layers to be reintegrated into soil pools in deeper soil layers as a proxy for sorption or microbial uptake?
Yes, I didn't see the question, but so I'm not an expert at all in how this works in theory, but I guess that's something we should do definitely afterwards. But I think there are so many things on the list that, yeah, I haven't looked into this.
Question? Are you raising your hand? Will.
Sure. Marius, do you have any idea if, I really like your simple approach, like we don't know what these numbers should be, we just want to generate fluxes. But do you have any idea if the concentrations you're getting of DOC in solution, either on land or in export, are at all reasonable? I don't even know what reasonable would be.
Yeah, so I've done a quick check for the 0.3 grams per liter, which should be fine as like a maximum value. And so this was actually, first I did not even have this accumulated pool in CTSM, but then I would have like a lot of DOC in desert regions where there was no water, and this DOC will just accumulate in Mozart and result in very, very high concentrations. So 0.3 is theoretically possible, at least. And then those tiny parameters that I have in the decomposition cascade, those are, so Dev, which was working before me on this project, had found these tiny parameters, which should be theoretically possible as well. It's just not very dynamic when we compare to Joules and Orchidae, which probably have like equation for DOC production, which is independent from decomposition and where it depends on temperature and water independently. So I would say that would be better, but like incorporating this in the cascade, which is already existing, is much easier than creating a new cascade.
Dave, it looks like you had your hand up.
It was, I guess, just a comment. We probably should talk with, developments of CTSM for CSM3. We're kind of avoiding those negative water states in Mozart because the ocean model doesn't like them, right? So we, understandably, so we should just talk, and there may be you may not have that problem anymore if you use our most updated parameter settings and nameless settings and things like that, right? So.
Thanks to all of our speakers. We have some time reserved for discussion. And then after that, Will is going to announce the recipient of the Slater Award. So that's sort of what remains before lunch. So if anybody has any big picture ideas or questions or comments that cut across some of the talks we've heard, we have some time for that now. Yeah, Nikki.
I was really excited about Charlie's simulation of net negative emissions that has a somewhat more realistic, although still somewhat unrealistic time evolution of the emissions. And I love the idea of having more CESM simulations that are emissions-based rather than prescribed atmospheric CO2 concentrations. And I can see how at least the ocean community could begin to use those simulations. And so I'd love to have a conversation with this working group about whether that's something we should be doing, whether we should try to get resources to do that. It's something that we need to understand better. And I'd love to be able to understand it better using CESM.
Can I respond to that? Yeah, that's a great point, and we have that discussion all the time. And so I do feel like one of the things we're going to try to do over the next year or so is get better at these emissions-driven runs. It's a goal of the Rubisco project as well, to do a whole new set of emissions-driven runs going out. In that case, in addition to doing new ones, doing them at low CO2 emissions levels, which we haven't really done, which I think where, you know, the mitigation efforts are more impactful probably, and also going out to 2300, which we also haven't done. So there is some sort of funding associated with the Rubisco project to try to, you know, I don't know, get more of the knowledge base out of Keith's brain and into a wider range of capabilities for that. So I do feel like that should be a goal.
Will those have you know, a smoother drop off in emissions? So CDR MIP, or it really is that like abrupt, just whoop?
These would be like SSP scenarios,
Okay.
so they'd be realistic.
Yeah. Okay.
We haven't decided exactly which scenario we're going to run, but just, you know, I think the only emissions runs we've ever done with CSM really has been the SSP5, like the really high. Keith, you can correct me if I'm wrong, but I think we've only gone for the really high one.
I think that's right. And there was some 1% versions. But even the SSP one had to be thrown away because of a bug in the aerosol forcing, and I'm not sure that it was actually ever redone.
Charlie posted also ZECMIP.
Yeah,
So Charlie showed simulations.
ZECMIP is the only other one, yeah.
That's right, Zach.
Do we understand that bug? Is it fixed such that it will not?
Yeah, it was a forcing issue with.
I want to say even there's like running them, and then there's just more people needing to look at what's happening in them. Because there's all kinds of emergent timescales of what's going on when you look at Charlie's plots of like global fluxes. But why are those the timescales, and what are they dependent on? I feel like nobody's even scratched the surface of looking at what that depends on.
Yeah, absolutely. Whatever we do would be a community run to, you know, for everybody to look at. So I think, yeah, I feel like it's important that we take the effort to try to be able to do these, right? Because now I think we're all a little bit fearful of them because they're hard to set up. And so we just need to kind of get over that.
This may be a really stupid point or question. Just sort of summing up what's been happening over the last couple of days and just my experience over the last couple of years, and still learning a lot about this model and feeling like I finally can do things with it, you know, that work. But there's also, at the same time, we have these, you know, there's lots of things coming at the model, most of which are like great. It's like, okay, we're adding processes that are important, we're refining processes, making it more realistic. But the model's still getting more complicated. And simultaneously, there's all these other approaches that are requiring people to run the model hundreds or thousands of times. We have to spin the model up more. We have to do, it just seems like, and people are always, you know, when you're talking about designing an experiment, people will say, well, you really should use an ensemble. You shouldn't just force this with one thing. You should force it with an ensemble. You should try different parameters. And it's just multiplying, you know, there's a lot of, we have the capacity and the understanding of the model to basically know you have to do more stuff, and but it makes it seem like things are just snowballing. And I know that's something that's probably happened through the history of all modeling, but my question is, within the community, how do people feel that things are getting simplified? You know, you can always find ways that things are getting more complicated, but how are we actually simplifying things and making it more manageable? Especially, you know, this is a tough thing when people come into the community. It can be very overwhelming to think about all the stuff you might have to do. There's no easy answer to that, but.
Holly has a comment on that.
Yeah, I'd say that two things that I've found extremely helpful, the new OPSI driver and being able to run a single point just by entering coordinates. That's been pretty much a game changer. And the subset data script. So I think there have been a lot of tools that have been worked on over the years. And like just this morning, I just used subset data and created a bunch of surface data sites for sites that I need to run. And it's just so much easier than it was when I started. So
Maybe the containerization is going to do the same thing. I feel like containerization could be a game changer, but I don't know yet.
Yeah, so Josh, that's really a great question, and I think, but I also want to get into more of a philosophical perspective too, because is something like fates making the model more complex, or is it making it more simple? Is the multi-layer canopy more complex, or it's more simple? You can actually think of those things as making it more complex, but what I was sort of saying in my talk is that the physics and physiology are more theoretically sound than what we have. So in some ways, it's simpler because you can actually sort of understand the equations that are in the model. I think the same is true with fates. It's more ecologically realistic. It's sort of trying to operate at the way in which sort of, particularly in forest dynamics actually works. Whereas in a biogeochemical model, you can't get that, so you just sort of try to make it work, and you're adjusting things all the time to try to get the right answer. And so I think in some ways, these models that are coming in are actually making it's complex in more lines of code, but it's simpler in terms of the theory that goes into these models.
Yeah, just a comment on that. There's been a lot of tools that have made it easier to run the model, which is really appreciated. My approach to it has been to come up with other types of ways to design experiments that get at the question you're trying to get at. And I agree that's not really accessible until you kind of learn how everything works together. But for example, the multiple complexity models, complexity modes in fates, like while they may be a little bit hard to understand at first, will allow people to more directly run a version that's relevant for the question that they're asking. Or we made a really simple land model. So I hope that those options give people a more direct path to answering the question they want to answer.
Charlie?
Yeah, on this point, and to Keith, one of your bullet points on your last slide about applying your Krylov method to fates. I mean, I do think that right now, because the set of people who are using fates is, still relatively small, and the spin up is difficult, right? And as we more people use it, spin up with fates is considerably slower than in the big leaf model, and that's going to get worse when we include nitrogen cycles and things like that. So I'm curious, like, if you've thought at all about how we might, approach the spin up problem better. If you had that bullet point in your talk for fates in particular.
Very little, very little thought. I'm not even sure how to compute an end state minus beginning state when you've got time varying cohorts. So in that, just translating when you've got the time varying cohorts, how to translate that into the mathematical language, that's not obvious to me. So I would have to understand how you even represent something like that.
Yeah, like we may have to create like a sort of some sort of translation layer from the cohort to like a vector of sizes, something like that, in order to mediate that.
There are issues even doing that we've got a new ocean model that has a time varying coordinate, and being able to compute an end state minus beginning state when you have time varying coordinates adds complexity. So.
Ryan adds that he thinks there's a way to translate cohorts into a vector.
In principle, the fate age structure is conceptually very similar to the soil age structure. It's just that we solve, in a sense, we solve the soil problem, with an Eulerian scheme and fates with a Lagrangian scheme. They're both just, partial derivatives in kind of age space. And so, theoretically, it seems like we ought to be able to find an analogous way, but because the solutions are so different right now, yeah.
right, we're sort of hitting up against our time, but we have a nice long lunch period. So I hope folks will stick around and continue these discussions at lunch. And now Will is going to present the Slater Award. Please.
There's a phone on the floor.
Thanks, Nick. Yeah, so before presenting the Slater Award, I also wanted to acknowledge especially Nick, who's been back in the booth, and the rest of the team behind the scenes, the AV crowd. Thank you very much. I'm super happy with how our first hybrid meeting worked, and I'm looking forward to be able to offer this in the future. Yeah, so I talked a little bit about the Slater Award earlier in the week, and we had a distinguished panel of scientists try to wrestle with, out of the 30-some presentations that we had from graduate students and postdocs, who really made some significant contributions to the working group. And so we were really impressed by the CLMU team, and this is kind of the first time we've ever given the award to a team. But we thought that Joyce Yang, Kathy Lee, Kier Zahn, and Bowen Fang. Bowen didn't present, but has been really integral in the development of the transient urban capabilities in CLMU. Really did a nice job. So our first award goes to the CLMU team. I don't know if they're online, but we can clap for them if they're not here. And also thanks to Keith for helping kind of steer this team in some really productive and exciting ways. And then also Joshua Rady. We wanted to give the award to you for really a long time that you've been contributing to this working group and providing thoughtful input and discussions, both in the FATES community and for CLM. So thanks. And we have a small token of our appreciation and a very fancy award.
Let's get a photo of him with his.
Oh yeah.
With his certificate.
Yeah.
Yeah. Well, thank you. Yeah, I've never won anything, so.
You're a winner.
Yeah.
Yeah.
An award speech.
Actually, we'll do it with Will.
Okay.
I've always wanted to.
There's more?
Okay.
There is more in there.
There is more.
Right, I'm gonna do a photo op here.
Sure. Yeah, I'll get it with Drew's.
Drew's picture. Okay, great.
Excellent.
Thank you. Thanks, appreciate it.
Yeah.
Oh, thank guys.
Yeah, that's it. So
See you after lunch for Ocean.
1:30 for Ocean BGC.
thanks.
This figure shows the CO2 emissions to the atmosphere and also the carbon sinks into the ocean and the land. So from this figure, we can see how much carbon is remained in the atmosphere and how much carbon could be stored in the ocean and in the land. So we are interested in the ocean carbon sink. This is because the ocean takes about 25% of anthropogenic CO2 from atmosphere over the industrial area. And this figure shows the mechanisms that can affect the ocean carbon sink are pretty complex. It is important for us to distinguish the natural carbon cycle and the anthropogenic carbon cycle. So if we look at the atmospheric carbon in the corner, we can see that in the pre-industrial era in steady state, the atmospheric CO2 concentration was either increasing or decreasing. So it's in steady state. And on top of that, we are imposing anthropogenic perturbation that sum with the natural carbon gives the total carbon in the atmosphere. If we look into the ocean, the total carbon in the ocean includes both the natural carbon and the anthropogenic carbon. And we see that in terms of the natural carbon, the biological pump is included in the natural carbon, and the carbon stored by the biological pump is also transported and redistributed by the meridional overturning circulation. And if we focus on the anthropogenic carbon, we can see that this part of carbon is not driven by biological processes, but it is driven by the rising atmospheric CO2, and it's also transported and redistributed by the meridional overturning circulation. So again, the atmospheric CO2 is the first driver of the ocean carbon sink. However, the ocean circulation patterns could also affect the ocean carbon sink by multiple ways. And this figure is showing the global air CO2 flux across multiple warming scenarios. And we see that there are great uncertainties of the size of ocean carbon sinks across CMIP6 climate models under each climate scenario. And we also see that under each climate scenario, the atmospheric CO2 in each model is the same. So the thing is, the large uncertainties are driven by ocean processes. And in this study, we pick up 3 climate scenarios from the most moderate warming scenario to the business as usual warming scenario. And for the models, we choose all the available CMIP6 models plus one specific Earth system model, CESM, and also an offline model to do this study. So the scientific question here is, how do ocean circulation changes could affect the ocean carbon sink in CMIP6 models and in the CESM under climate change? So here is my results. The first figure showing here is the changes of both AMOC and ISMOC along climate changes under different warming scenarios from SSP 1.2.6 to SSP 5.8.5. So AMOC and ISMOC is the upper and abyssal cell of overturning circulation. You can look into this schematic. So we see from this figure is the meridional overturning circulation slows down both in the upper and in the abyssal cell, no matter in which warming scenarios. But the strength of the slowdown will highly depend on the scenario. The overturning circulation will slow more under high-end warming scenario, but it will slow slice under moderate warming scenario. And to the year 2300, there are only around five swirl drop AMOC left under business as usual warming scenario. But in terms of the ISMOC, which is the basal cell overturning circulation, we see that it almost fully shuts down. So the next question is, we are curious how the slowdown of overturning circulation, especially the abyssal cell of overturning circulation, could affect the strength of the ocean carbon sink from pre-industrial to the year 2100. So in this study, we're trying to separate the role of ice mark slowdown on the biological pump and the solubility pump to affect the ocean carbon sink. So the first way is the ice mark slowdown will affect the accumulation of the regenerated carbon. This is how I define the biological pump and finally affect the ocean carbon sink. And the second pathway is how the ice mark slowdown could affect the accumulation of preformed carbon, which is the strength of the solubility pump to affect the ocean carbon sink. So this figure shows the changes of ice mark, AMOC, and the ice port production at 100 meters in each individual CMF6 models. So we fully studied 13 CMF6 models to include all available models that we can do, and we noticed that almost all CMF6 models show larger slowdown of AMOC and IceMOC under high-end warming scenarios than moderate warming scenarios. See the panel A and panel B here. And we also noticed that all CMF6 models show decreasing biological carbon exports with larger declines under stronger climate warming. The next figure, we show the accumulation of preformed carbon and regenerated carbon in the ocean. And the upper panel, the top row here shows the accumulation of the preformed and regenerated carbon at intermediate depths from 100 to 2000 meters. And the bottom panel here shows the carbon accumulation in the deep ocean. And we see that almost all CMF6 models show increasing preformed carbon, which is panel E and G, and regenerated carbon, panel F and H. But we can also notice that the preformed carbon accumulates more in the intermediate depths, but in terms of the regenerated carbon, it accumulates more in the deep ocean. The next figure, we are trying to understand how the IceMOC slowdown could affect the accumulation of regenerated and preformed carbon across all the CMF6 models. So this figure here shows the changes of ice port production over the changes of IceMOC versus the accumulation of regenerated DIC in the full water column of the water. So we see there is a strong negative correlation under each warming scenario, and the number in this figure shows the number of the models that we are analyzing in this paper. And we see that this negative correlation indicates that the increase of ice port production and the slowdown of IceMOC, they both contribute to the accumulation of regenerated carbon. And the middle panels here showing the changes of IceMOC versus accumulation of preformed carbon in the full column of the water. And we see there is a positive correlation. This positive correlation shows that the more slowdown of IceMOC will lead to less accumulation of preformed carbon. So this part showing how the slowdown of IceMOC will contribute negatively to the strength of the solubility pump. And the last panel here shows the net effect. That is how the slowdown of overturning circulation could affect the total carbon uptake in the ocean. So we still see there is a positive correlation that indicates the net effect of slowdown of IceMOC will reduce the strength of the ocean carbon sink. So, and then we focus on one specific model, CESM, to study the mechanisms, the details of how the overturning circulation slowdown affect the ocean carbon sink. So the left panel here shows the total carbon and regenerated and preformed carbon accumulation in each century. And the last two columns here shows the nutrients redistribution in the ocean. And we see that the accumulation of carbon is initially larger in the surface ocean, but because it's coming from the direct uptake of anthropogenic CO2 from the atmosphere. And we see that the strongest accumulation rate will progressively shift to the intermediate depths. But the preformed DIC dominates accumulation at the intermediate depths, but little has reached into the deep ocean, even by the year 2300, largely due to the slowing overturning circulation. And if we focus on the nutrient distribution, we can also see the overturning circulation slowdown could sequester more nutrients in the deep ocean. However, this will reduce the nutrient supply to the surface, which will further reduce the export production at around 100 meters in the ocean. And the last figure here, I'm trying to separate the role of slowing overturning circulation with the decreased biological productivity to further understand how the circulation changes could affect the strength of the biological pump. And the three schematics shows the biological and the circulation contributions to the regenerative carbon accumulation in pre-industrial and in 21st century and 23rd century. So we see that the overturning circulation slowdown will lead to the ocean will sequester the nutrients in the deep ocean. This will further decrease the export production. So we see the biology part will keep decreasing as climate warms compared to the pre-industrial level. However, the circulation slowdown could also allow the carbon to stay in the ocean for a longer time, so that we see the removal of this carbon from the ocean back into the atmosphere will also decrease. This will lead to a net positive regenerated carbon accumulation in the ocean. And the net effect of overturning circulation slowdown to the biological carbon pump is the overturning circulation slowdown could help the ocean to accumulate more regenerated carbon at depth. And so here is a summary. The slowdown of overturning circulation depends on the scenario, and it slows more on high-end scenarios, and it slows less on the moderate scenarios. And also we see the slowdown of SMOG will decrease the export production, but increase the carbon sequestration time in the ocean. So the net effect will accumulate more regenerated carbon in the ocean, or the strength of the biological pump will go up. But the slowdown of overturning circulation will finally reduce its accumulation of the preformed carbon in the oceans, even though the specific mechanisms are not very well understood. And the net effect is the slowdown of overturning circulation will reduce the size of the ocean carbon sink, and this will explain around 1/3 of the spread across all the CMIP6 models. That's everything I want to present, and feel free to ask any questions. Thanks.
Thanks. Thanks, Yi. I think we have time for just one question.
Mm-hmm.
Nikki.
I have a clarification question. Can you hear me, Yi?
Yes.
When you're estimating the changes in the nutrients using the transport matrix method, I'm confused about this because my understanding of this is that this is a steady state ocean the transport matrix is based on a steady state ocean circulation, yeah?
The transport matrix is based on the time evolving circulation. So I have the transport matrix each year from pre-industrial to 2300. So we have the change in circulation, yes.
Okay, thank you.
Mm-hmm.
Okay, let's move on. Our next speaker is Jun Yu. Ready? You're online. June, you can share your screen. Can you stop sharing?
Yeah, I stop here.
June, we can't hear you. It doesn't look like you're muted though.
Share your screen.
There you go.
Screen.
You're having trouble sharing your screen. Okay, why don't we switch the order of the talks, and you can work on that while Nicola comes up. Okay, June, we're gonna have Nicola present, and you can figure out how to share your screen in the interim. Is yours on here?
Should be.
That's all what the.
Great. Okay. Hi, everyone. I'm Nicola Wiseman. I'm here from the University of California, Irvine as well. And today I'm going to be presenting some results that I have using CESM 1BEC, where we're trying to quantify the feedbacks between phytoplankton elemental stoichiometry and marine biogeochemical cycles. So this group of people is going to be very familiar with the sort of context for this research. So we know that carbon export is linked to nutrients via stoichiometry. Okay. Cool. Great. Yeah, so we know that carbon export is linked to nutrients via stoichiometry. And the portion of the biological pump that I'm going to focus on here is phytoplankton photosynthesis and uptake of nutrients and incorporation into phytoplankton biomass, or their elemental ratios of carbon, nitrogen, phosphorus, iron, and silica as well. So here's sort of the area that I'm going to focus on. So what I've been working on the past couple of years is implementing a variable nitrogen quota into CESM BEC as well as CESM Marble. And we know that phytoplankton carbon, nitrogen, phosphorus ratios play a key role in the coupling of carbon, nitrogen, phosphorus cycles with significant variations in different ocean environments. This has been pretty well observed at this point via ocean observations of cellular stoichiometry as well as particulate organic matter stoichiometry. And that variations in phytoplankton nitrogen phosphorus are pretty directly tied to nitrogen phosphorus supply. So what we want to know is what impacts does variable stoichiometry have on the sensitivity of biogeochemical cycles? So why do we need variable C to N in models? Well, we know that variable C to N tends to vary a lot less than C to P, but quite a few different our system model studies have found that using fixed red field C to N in models ends up underestimating the ocean DIC inventory, and that the marine nitrogen cycle is more sensitive to biological processes when variable C to N is included. And we care about the marine nitrogen cycle because it's really key to global net primary productivity, as much of our global oceans are nitrogen limited, and therefore that perturbations to nitrogen export and nitrogen fixation affect the global nitrogen supply. And we also know that denitrification is very sensitive to export and oxygen, and it is highly variable within our models and sort of poorly constrained. So here's the version of CESM I'm working with. This is CESM BEC 1.98. We have our 3 phytoplankton groups, our small phytoplankton, diatoms, and diazotrophs with fully variable carbon, nitrogen, phosphorus, iron, and Si. And we have a variety of iron sources that have mostly been updated to resemble that of CESM2. So we have atmosphere, sediments, rivers, as well as hydrothermal vents and bottom scavenging. So we have a fairly robust marine ecosystem as well as iron cycling. So what we did is implemented a parameterization where phytoplankton growth is a function of, or phytoplankton stoichiometry is a function of the following, where the X stands for whichever nutrient it is, so nitrogen, phosphorus, iron, Si. So basically, what we have is when we have a lot of a nutrient X, then our phytoplankton are setting their ratio at the highest possible nutrient to carbon. And then when the ambient nutrients fall below a prescribed optimal value, the phytoplankton begin decreasing their nutrient to carbon ratios until they hit a prescribed minimum. And so this is how all 4 of these nutrients are now represented in the model. We also have some added complexity where, for example, for the P quotas, when nitrate is low, we reduce both nitrogen and phosphorus uptake in order to maintain N to P uptake that is appropriate for ambient phosphate levels. And then we also have an added sort of complexity for our Si, which is when Si is when there's a lot of, or when the dissolved Si concentration is lower, you have lower Si to carbon. And when it's replete but iron is lower, you get a further increase in Si to carbon. And that's sort of based off of some physiological studies. So these are the ratios that we have currently implemented into the BEC. So each group of phytoplankton has their own prescribed range, which have been constrained from the GoShip POM observations. Oh, this is okay. The Tanioka et al. Is now published. It was published last year. And then we have our N to P, we constrained from inverse model estimates, such as Wang et al. 2019. And then the iron to carbon range was constrained by observations from Ben Twining and others, and is reported in a paper that I have that's currently in review. So each group has their own set ranges, and they're specific to each group and informed by physiology. So here are the context of my simulations. I've got constant pre-industrial CO2 run up 300 years, averaged over the last 20 years. We have a fixed model where the C to N to P is fixed at 96 to 16 to 1, iron to carbon 7, Si to N is 1, and then our variable stoichiometry that I reported on the previous page. And all units are typical. And then we have our POM database. This is just showing where our observations are from. And I'm going to be comparing these observations to CESM export at 100 meters, which does not account for heterotrophic bacteria and detritus that is present in the POM observations. So that is an important consideration, is that we can't really expect to match these observations directly. So here we have the observation and phytoplankton observations in blue, export in red, phytoplankton in black, showing the C to N and C to P versus dissolved inorganic nitrogen and PO4 at the bottom. So in general, we have our phytoplankton have much higher carbon to nitrogen than our export, and there's sort of general agreement between our POM observations and our export ratios, because those are the closest comparisons to make. And then we also have our C to P as well. And one thing to note is that our C to P in the export here is low, and that is, I got these results last night, and so that will be definitely addressed in a run that we have already submitted. So these aren't final results yet. Here we have global maps of, this is the export at 100-meter carbon and nitrogen, and then overlaid in squares are our observations. So as you can see, we get general agreement in the patterns of our carbon and nitrogen, especially if you look at our Pacific cruise there, that's P18. We see lower carbon to nutrient values in the equatorial upwelling region, and then elevated values in the South Pacific Gyre. We can see as well in sort of patterns in the North Atlantic gyres as well, where we have elevated C to N gyres and lower as you move towards the Southern Ocean. Here is our C to P. So again, we see sort of general agreement. As I mentioned, our C to P is too low here and will be fixed promptly. But we are getting the sort of general patterns that we see that are primarily as a result of the surface nutrient fields. Here's a specific cruise transect. So this is that P18, that Pacific North-South cruise. So going from south to north, and we have our C to N, N to P, C to P, our nitrate, dissolved iron, and phosphate. For blue is our observations, and yellow is our model. And for the model, I'm showing in the dotted line is the just combined zoo and phytoplankton, and in the yellow line is the actual export. So you can see that those lines are actually quite similar here, and it's usually, in a previous version, they weren't as similar. But in general, we see, we're getting that pattern of elevated values in the gyres, which we want to see. We're reproducing our observed nutrients quite well. And the low N to P is driven by the low C to P, whereas our C to N actually, I think, looks the best it ever has, which is nice. And so here we have our actual sort of science results. We have the comparisons of our phytoplankton surface nutrient limitations for a fixed stoichiometry and variable stoichiometry scenario. We can see for our diatoms, we get a transition from nitrogen limited in most of the gyres to primarily SI limited, as well as expansion of our P limited regions. And we also see large increases in SI limitation where iron was previously limiting. We have the same for our small phytoplankton. Again, in our fixed stoichiometry, you see that expansion of P limitation. This is most likely because our phytoplankton have far greater P flexibility than N flexibility. So when you fix both N and P, the rigidity of that P quota dominates the sort of patterns of limitation. And then for our nitrogen fixers, we see sort of increases in the severity of our P limitation in the Atlantic, for example, as well as reductions in the sort of regions that are replete. So here are some impacts on sort of globally integrated fluxes for our variable and fixed scenarios. So for net primary productivity, we actually see a slight increase when we use our fixed with an increase of roughly 3%. For our POC export, we see a decrease in 10%. For nitrogen fixation and water column denitrification, we see much more drastic decreases of roughly 25 to 54% for both. So when we're using this sort of fixed stoichiometry version model, we are really underestimating these key nitrogen fluxes. Other impacts, there were significant changes to the community composition when fixed stoichiometry was used. So for example, in our variable run, our gyres had up to over 15% diatom composition compared to the small phytoplankton, whereas the diatoms almost disappeared from the gyres entirely in the fixed model. We also saw a global increase in the N-star bias, greater than 20, with positive N-star values in all ocean gyres in the fixed run from 0 to 315 meters depth. Part of this is exacerbated by the N to P being too low in our export, but still, because we see that change from a normal negative N star in the global ocean to positive everywhere. We still expect to see a bias. It just will be probably slightly smaller. I also did some additional experiments. These are new. The fixed SI, I think, probably finished this morning, but I didn't get it in here in time. But so I iterated where we fixed only one nutrient at a time to sort of try to pull out, which nutrient being fixed has the greatest impacts for those same majorly integrated fields. And as you can see, an interesting result is that our fixed nitrogen actually results in increases in some of our carbon and nutrient fields. NPP and POC flux don't change much, but our nitrogen fixation and water column denitrification do increase slightly. Whereas with our fixed P, we see those decreases in POC export and fixation and water column denitrification that dominate when you fix all of the ratios. And the fixing of the iron, the impact of that on the nitrogen cycle is something that is explored in the paper that I currently have in review, so I didn't really go into that here. So in general, dynamic stoichiometry is necessary for understanding interactions in ocean biogeochemistry. Changing stoichiometry is likely to modify climate change impacts, and fixed nutrients can have opposing impacts on the BGC cycling. And hopefully we will have our final version of this soon, and we'll be submitting it thereafter. So thank you. Questions? Yes.
Go ahead, Nikki.
Okay. Is it safe to assume that because NPP and export don't change very much, that the DIC doesn't change very much? So early on in your talk, you sort of motivated it by saying it could have an impact on carbon, but.
Yeah, so that's a great question. That would be my assumption, and I would need to actually look at the total DIC inventory, but that's something that we're interested in, is because some of these studies that have done comparisons of fixed and variable stoichiometry see competing conclusions, where some see increases, some see decreases. And so we're hoping that a lot of those have focused on either fixed C to N or fixed C to P, but not fixing and variable both. So that's something that we hope with this research we can give some more insight into.
Any other questions? We have time for maybe one more. Okay, thanks, Nicola. Okay, next up, June, I hope you figured out how to share your screen. And you can do so now and begin presenting.
Can anyone see it?
Yep, we can see your slides. You're not in. You're not.
What about?
There you go. That's great, and we can hear you too.
Okay, so hi everyone. My name is Jun. I'm a second-year PhD student in UC Irvine, working with Professor Kismore. We are collaborating with CSM2 Marble developers in Ankara about expanding the marine ecosystem on Marble. And this project is still ongoing, in progress. So we just wanted to share some preliminary results here. So first, let me start with the big picture of why we need to do this. So the biological pump plays a critical role in storing carbon from the atmosphere, and the efficiency of the biological pump is largely controlled by the ecosystem community composition. So as we can see in the, where's my mouse? So as we can see in the stratified oligotrophic ocean, that kind of ecosystem is dominated by the smaller size phytoplankton and zooplankton. As a result, the POC export is kind of weak. But in the mesotrophic and eutrophic ocean, that kind of ecosystem is dominated by the larger size phytoplankton and zooplankton. As a result, you can see the POC exports stronger, and the strength of biological pump is also stronger. But if we look at the 2-degree warming in the future, we can see that the global warming will cause the global ocean to be more stratified, and the oligotrophic condition will also expand globally. As a result, in the region previously is dominated by larger phytoplankton and zooplankton. In the future, it will not be the same. It will be the ecosystem will shift to the smaller size phytoplankton and zooplankton. So we can see that such condition will largely hurt the strength of the biological pump in the future. So there's a question mark here. How much uncertain do we know about the future changes in the marine carbon export? So in the recent paper from Hansen 2022, and it showed that the prediction in POC export in the current CME6 models do not agree with each other, both in terms of the future change, the direction of the change, and also in terms of the magnitude of the change. And is mostly the many reasons can cause that, and the main reason is that there the marine ecosystem representation in this most of the CME6 model are very simplified. There's lack of plankton size diversity there. Typically, it only includes 2 to 3 types of phytoplankton and 1 to 2 types of zooplankton. And such simplicity will introduce uncertainties of the estimation of future changes of POC export. So here we believe that there's an urgent need for global climate models to have a more sophisticated representation of multiple plankton functional type in the marine ecosystem models. So we are currently working on expanding the marine ecosystem on Marble with the intermediate complexity so that we can use this model to do future climate runs. And here, this slide is showing the latest version of CESM2 marine ecosystem model. It includes 4 types of phytoplankton, which is picophytoplankton, diazotroph, cacalysophores, and diatoms. And it only includes 1 generic zooplankton group, so it looks pretty simple, right? So in our current new ecosystem model, which is AP4Z model, we expand the marine ecosystem. For phytoplankton, we have 8 different types of phytoplankton, and also have 4 different types of zooplankton. For the pico-sized phytoplankton, we have Prococcus, Synechococcus, picoeucaryotes, and small diazotroph. And for nano-sized phytoplankton, we have Phytocysts, cacalysophores, and other generic nanophytoplankton. And for the micro-sized phytoplankton, we have the classic diatom to represent that group. Besides phytoplankton, for zooplankton, we have 4 different types of zooplankton, and includes small and large microzooplankton, and mesozooplankton, and macrozooplankton. So the 2 microzooplankton are the main grazers for the smaller size phytoplankton, and it also is the direct linkage between the primary producers and the higher trophic levels. And for the 2 larger size zooplankton, they are the main grazers for the larger size phytoplankton. And they are also the main food source of the fisheries. So this model also have the potential to provide insights for the future fishery yield. So in this figure, you can see there's a complicated marine food web showing here. So how did I assign this complicated grazing relationship? And the answer is that I followed the previous study about the optimal predator to prey size ratio. For example, the Z1, the size of this zooplankton is about 2 to 20 micrometers, and the food they most likely to prey on is about the size of that food is about 10 times smaller than that. So based on this grazing relationship, based on the optimal predator to prey size ratio, we assign this grazing relationship to our model. And here is the most exciting part, the model performance. So this slide shows the model validation between the in situ phytoplankton biomass and the model results. So on the left, is the global data set for the 3 picophytoplankton. And we can see that model generally reproduce the spatial pattern of the these 3 pico-sized phytoplankton groups. Shows Prococcus dominating in the subtropical region and Picoeucherios dominating in the higher latitude. And on the right is the institute data set of the larger size phytoplankton. Although the data is kind of sparse, but we can still see that our model capture the general pattern. Like the model diatom is showing a higher value in the subpolar region and lower values in the subtropical region. And also in the coastal region, the model captures the higher value for the fire synthesis and is the same with the institute data. And here is the comparison with the satellite-derived phytoplankton biomass across the 3 different size phytoplankton groups. So on the left is the previous version of CESM2 model. And in the middle is the satellite data, and on the right is our AP4Z model. So we can see that previous model didn't really capture the higher value for the picophytoplankton in the higher latitude, and our AP4Z model it captured the higher value for the total pico C in the higher latitude, and also our total nano C and the diatom C also shows similar pattern compared with the satellite products. And this figure shows the percentages of the 3 phytoplankton groups relative to the total carbon biomass. So we can see that both model and the satellite shows picophytoplankton is dominating in the subtropical region. It's about higher than 50% of the total biomass, and the nanophytoplankton and microphytoplankton is co-dominating in the higher latitudes. And this slide shows the comparison between the modeled total chlorophyll and the satellite chlorophyll. So we can see our model capture really well of the spatial pattern and the magnitude of the satellite chlorophyll, and the biomass is within the reasonable range. And on the right is the total NPP and also the group-specific NPP. You can see that total NPP is in the reasonable value. It's about 50 pg per year, and also we can see different the NPP from different group is also showing a reasonable pattern, such as phytoplankton is the dominant species of the total NPP. Is about 60% of the total NPP, and the nanophytoplankton and the microphytoplankton is kind of like the same. Similar range is about like 18% of the total NPP. And this figure showing the model, the zooplankton distribution. And we can see that the modeled zooplankton shows a similar spatial pattern compared with the Murdat in situ biomass. And also the depth integrate carbon biomass is also within the range of the value from the observations. So here's a summary of this project. Currently, we are developing intermediate capacity marine ecosystem model within the CESM2 marble, and it has the potential to do climate runs. And the current AP4Z model can reproduce the general pattern of the observed phytoplankton groups, and it's showing picophytoplankton is dominating in the subtropical region, and the nano and the diatom is co-dominating in the higher latitudes. And our simulated zooplankton groups is also showing a good agreement with the observations. And finally, is the implication for this model. So this model can help us to study how plankton size and also community composition impact carbon export and the CO2 flux in the future. And also this model can help the future studies to incorporate more key missing process in the ecosystem, such as zooplankton vertical migration. And also this model allows for the future ecosystem extension for fisheries and also other higher trophic levels. Thank you. Any questions?
Thanks, June. Are there any questions? Anybody other than Nikki?
Just trying to keep it lively here.
Okay, go ahead, Nick.
Do the NPP estimated by the 8P4Z model is about 50, right? From the 4P1Z model, isn't it quite a bit higher than that? If I remember right, like in the 60s?
I remember kind of similar. I remember the spatial pattern is very similar to the satellite MPP, but I didn't sum up together. I don't remember the exact value actually. Maybe Christine know that.
Low 60s, maybe. It's interesting that by adding additional PFTs, the MPP went down. Yeah.
Okay, any other questions for June? Okay, we're going to take a 15-minute break and return, well, not quite 15 minutes. We're going to return here at 2:30 for Genevieve's talk.
All right. Hi, everyone. My name is Genevieve Clow. I'm a grad student at CU Boulder, and I'm advised by Nikki Lewandowski and Jen Kay. I want to start by thanking them, along with our collaborators at NCAR, Mike Levy and Keith Lindsay. Today, I'll be presenting our... Sorry.
You want it to be picking you up.
Okay.
So actually higher.
Okay. How's that? Better? Okay. All right, so I'll be presenting our project, implementing a satellite emulator in CESM2 to evaluate the impact of clouds on ocean chlorophyll observations. Phytoplankton are vital for marine ecosystems, and they're also a key part of the climate system due to their role in the carbon cycle. So we care a lot about the spatiotemporal distribution of phytoplankton. And the main way that we study phytoplankton populations on a global scale is through remote sensing of chlorophyll, which is their primary photosynthetic pigment. And to detect chlorophyll, we rely on visible green and blue wavelengths. So since we're using the visible spectrum, we are unable to detect phytoplankton in the absence of visible light or beneath cloud cover. Unfortunately, if we look at these two model climatologies of chlorophyll and clouds, we see that regions with high chlorophyll also tend to correspond to high cloud cover. So therefore, we are unable to reliably detect phytoplankton from satellite observations in the regions where they are most abundant. Here's an example of some real-world data. The missing data is shown in white here, and these are two 8-day composite images. You can see that even after 8 days of sampling, there are still significant data gaps, and a lot of these data gaps are due to clouds. However, there are other factors that prevent satellite detection as well. In the high latitude winters, we see that there are no observations at all, and this is because there just isn't enough light for satellite detection. So in order to create a more direct comparison between the full field model outputs and these satellite observations, we developed a satellite emulator for chlorophyll in CESM. So now the model generates the standard total chlorophyll output in addition to these simulated observations of chlorophyll. So we can use these simulated observations and compare them to the total chlorophyll output to assess potential biases due to missing data. So right now in the emulator, we have included several factors that prevent satellite detection. We have clouds, sunlight, and sea ice. However, as I mentioned before, there are other factors that also prevent satellite detection that are not included yet, but may be included in a future version of the emulator. So our new model output is generated within POP, but we needed to pass in several other variables from different components. So here we use sea ice, and then from CAM, we passed in the solar zenith angle and the simulated cloud observations from COSP. And then using these new variables, we calculate a weight for each grid cell in POP, which is the total fraction of a grid cell that a satellite would have been able to see. And then we apply these weights to the total surface chlorophyll, and we end up with our satellite observed chlorophyll. So these are the details for our initial CESM run. We tested the emulator with a 50-year pre-industrial control simulation. And here I'll show results from the last 30 years after we made sure that the surface chlorophyll had reached equilibrium. So before jumping into the full results, I wanted to show a brief case study comparing the satellite data, real-world satellite data to the emulator. So here I'm showing the mean seasonal cycle over the North Pacific. And I want to focus on the blue line here, which is the % missing data for a given day. And we can see that the emulator is doing a pretty good job at capturing the seasonal cycle of missing data. But it includes slightly more data than we would see in the real world. So the results that I'll be showing are a conservative estimate of biases due to cloud cover or missing data in general. So here are our results from the 30-year climatology. This plot is showing the impact of clouds on the chlorophyll climatology. So throughout my results, I'll be talking about the cloudy chlorophyll and the baseline chlorophyll. Both of these outputs include masks from the sea ice and daylight, but the cloudy chlorophyll obviously includes clouds and the baseline does not. So I'm trying to isolate the effect of clouds here. And you can see that the differences in the climatology can be quite large in certain regions. So far, what I've found is that this has to do mainly with the seasonal phasing of clouds and chlorophyll. So for example, in the North Pacific off of the coast of Japan, in the winter when we have low chlorophyll values, there's high cloud coverage. And then in the spring bloom, when chlorophyll values peak, this corresponds to low cloud cover. So we're sampling much more frequently in this time of the year, leading to an overall overestimate of the chlorophyll there. And in the blue regions, we see the opposite pattern. We were also interested in looking at the mean seasonal cycle over various ocean biomes. And you can see that the impact of clouds varies between these different biomes. And it not only affects the magnitude of the seasonal cycle, but it can also impact the timing of the peak bloom. And we found that these patterns largely emerge due to the spatial correlation within biomes between chlorophyll and clouds. So for example, in the Southern Ocean, regions that have high chlorophyll also tend to correspond to low cloud cover. So when we take the average over the biome, we end up with an overestimate of the total chlorophyll. And I also wanted to note here that you can see how the cloudy chlorophyll has a higher variability than the full field baseline output. All right, so far I've talked about how we've used this tool to assess biases due to missing data from cloud cover, but there are several other applications that I want to mention. The first one is model tuning. So here I'm comparing the model climatology to our real-world observations. And on the left side, I used the total full field model output, which is what we typically use to compare with observations. And then on the right side, I have the climatology calculated using the simulated observations, which is a more direct comparison to our real-world data. And so what this plot suggests is that the actual bias in our model may be greater than we previously thought. Another application that we envision this being used for is a gap-filling testbed. So in the real world, we often want to try to fill in the gaps in our satellite data. However, we don't have a ground truth to be able to validate these results. But in the model world, what we can do is fill these data gaps using various gap-filling techniques. And then we can compare this interpolated result to the model truth. In here, I've done a linear interpolation, but ideally, we would want to test this with many different methods to evaluate which one does the best, and then hopefully apply that method to the real-world satellite observations in order to improve that data set. And the last application that I want to mention is calculating the emergence of a trend. So when will we be able to detect the signature of climate change within the satellite-derived chlorophyll record? And here I'm showing the number of years that we would need to observe in order to say that the trend is statistically different from internal variability. So the trend, or the time to emergence, depends largely on the variance within our data set. And here we found that the cloudy chlorophyll has a much higher variance, and so this leads to a longer time to emergence. So this could be important for helping us interpret the trends that we see in our real-world satellite data. All right, thank you so much. I'll end here and leave this up for any questions.
Okay, questions for Genevieve?
sorry if you mentioned this and I missed. Is this done inside the model online, or you do online?
Yeah. Yeah, in POP.
Thank you.
Great.
I also may have missed something, but the schematic here suggests that you're sort of sampling swaths within the model. Do you actually have the orbit geometry built into the emulator?
We do. We have a simplified version of the Aqua Modus sampling pattern, which samples at 1:30 p.m. And it's not a perfect representation of the orbital pattern because we're not including orbital gaps between the orbits. So we actually tested a few different versions of this, and the results that I'm showing here are not from that version, but we are planning to look into that more and publish that in our paper.
I mean, having just that orbital geometry thing would be very nice for using this on other, other sensors.
Yeah, definitely.
What does a negative time to emergence mean?
Oh, yeah, so sorry if that wasn't clear. So in the bottom, I'm showing the difference in the cloudy chlorophyll time to emergence and the baseline. So that means that the baseline actually had a longer time to emergence.
Any other questions? Okay. Great. Thanks, Genevieve.
Thank you.
Our next speaker is Samuel Mogan. And back to you.
Amplified at all? Cool. Hey everyone, I'm Sam Mogan, use he, him pronouns. And before I get started, I just want to say thank you to my advisor, Nikki Lewandowski, and all of my co-authors, quite a few, and they're all listed right here. I won't read their names. Today, I'm going to be talking about ongoing work we have, trying to make skillful predictions of multiple marine stressors in the surface and subsurface ocean using CESM SMILE, the Seasonal to Multi-Year Large Ensemble, and some novel observational products. So I think we're all super familiar with climate change in the ocean, but just as a review, 3 stressors we're really interested in is heating, the ocean's growing warmer, decline in oxygen stocks around the ocean, and then acidification in the ocean. So we know these long-term trends, and we have a lot of models telling us about these long-term trends in the ocean. But here in the study, we're really interested in trying to make predictions on shorter turn time scales from months to years in advance. You can imagine these would be important for fisheries managers who are trying to understand how they should manage a fishery over the coming months and years. So we're trying to make these predictions on short-term timescales, and we want them to be relevant for fisheries. So where are we actually going to predict these stressors, or try and predict these stressors? We're going to focus on important fisheries. So on this map here, we're showing regions where fish catch is greater than 1,000 metric tons in 2015. So you see primarily all of these fisheries and fish catches happening in coastal regions. And these coastal regions are really captured in these divisions called large marine ecosystems, which I'm sure a lot of us are also familiar with. So we're trying to make these forecasts in large marine ecosystems. And in this study, we're going to focus on the North Pacific. Why are we going to focus on the North Pacific? Well, when we're making forecasts of biogeochemistry, we're really, really limited by observations. The carbon and oxygen in the ocean are relatively undersampled compared to things like temperature, which can be observed at the surface through satellites. So we're relying on these brand new products developed by Jonathan Sharp at PMEL and Liddy Kepler at Scripps, who have taken all of the observations we have for DIC and for oxygen over the last 20 or so years and developed machine learning algorithms to create these gap-filled products for the first time that are allowing us to look at gridded products for DIC and oxygen in the surface and in the subsurface ocean down to 1,500 meters. So these new products are really exciting. And one limitation of these, of course, is that the observations are still relatively scarce, even with machine learning algorithms. So if we want to look at high-resolution regions in these smaller locales, like a large marine ecosystem, we want to look at regions where there are a lot of observations being trained into these machine learning algorithms. So on this map, we're just showing regions where there's a lot of information and direct observations going into the machine learning algorithms and these data products. Here you can see a few regions pop out, a few large marine ecosystems. Sort of in the North Pacific, we see the California Current in the Gulf of Alaska, and we also see the Kuroshio Current, along with a few other regions in the global ocean. But for this talk today, we're going to primarily focus on these 3 North Pacific large marine ecosystems. How are we actually going to make these forecasts? We're going to use the community year system model, seasonal to multi-year large ensemble. Briefly, CESM SMILE works by first creating a historical reconstruction of the ocean and sea ice component of CESM using historical atmospheric and terrestrial forcings. Here we're just displaying carbon in the ocean, the surface ocean, over the last 20 or so years from CESM FOSSE. You can see it's going up as it is in the real world. And at various points, we initialize the model, and we stop giving the model real-world forcing and allow it to split up as a fully coupled Earth system model run. And each of these, at the beginning of each of these initializations, we slightly perturb the atmospheric temperature, generating an ensemble, 20 ensemble member, basically. So we have these 20 ensembles as our forecasts, and our most reliable forecast is going to be the average of all these ensemble members, as with other forecasts. And then we can take these forecasts and compare them to observations. Right here, we're just comparing them to observations from the FOSSE reconstruction, but we could also compare these to real-world observations to determine how well we're predicting things in the near-term future. So looking at results, we'll just start by looking at one example, and this is SST forecasts in the Gulf of Alaska. On the y-axis, we're showing forecast skill, just the anomaly correlation coefficient, or Pearson's R value. A high value close to 1 is a really good forecast. Value close to 0 is not a very good forecast. And on the x, we're showing at different lead times. So the further you get to the right, the farther you are from initialization. We expect these values, these skill values, to drop as we get further from initialization. We're just further from the real world. But here we're seeing really, really high skill forecasts out to about 8 months in the Gulf of Alaska. So this forecast is great, but we would need something to reference it to see how useful it is. So we then compare it to a statistical persistence forecast. How well do observations today predict observations tomorrow? On this plot, we're doing really a lot better than our persistence forecasts. And if these dynamical forecasts are going to be useful on these short-term timescales, we really want them to be beating these persistence forecasts, which are already often used by marine managers. So zooming out a little bit and looking at all of our tracers, we're looking at temperature in the left column, carbon in the center column, and oxygen on the right column, at the surface in the top row, and at 300 meters depth. So we'll start by just looking at skill in the surface in the Gulf of Alaska. So we see our solid lines are doing quite well, especially as compared to our persistence forecasts. We start to see drop off over time, but we have really high forecast skill values over time. If we move down to the subsurface ocean and compare that, you see we have slightly lower skills right at the first moment of initialization, but over time there really is no skill degradation. And you can see up to 12 to 13 months, we have really, really high skill forecast values that are beating the persistence forecast really handily in the subsurface ocean. So the Gulf of Alaska, very, very exciting results. Let's move down to the California Current. California Current, slightly different. We have really, really high skill forecasts for temperature and oxygen in the surface ocean. Carbon, a little less promising with our persistence forecast generally beating our dynamical forecasts. And at 300 meters, we again see some longer persistence of skill, but the values are slightly lower. Finally, we're going to look at our third large marine ecosystem, the Kuroshio Current. In contrast to the Eastern Pacific, where we have a lot of skill, we find a steep drop-off in the Kuroshio Current. In the surface ocean, we have some skill for temperature and carbon. But as we move down to 300 meters, we find almost no skill. There really is no skillful forecast in the Kuroshio Current subsurface. And we think this is related to both the limitation in observations of the subsurface Kuroshio Current and just the way it's represented in our Earth system model run. So we've looked at these time series, but in a little more digestible format, what forecasts are actually useful? How many months of these in 1 year do we actually have a skillful forecast? So on here, I've shaded each of these 3 large marine ecosystems that we're interested in by how many months we have a skillful forecast. And a skillful forecast here we're defining as an R value above 0.5, so it's just generally a high R value, combined with beating or outperforming a persistence forecast. So we have these 2 things that it needs to beat. And you'll find in the Western Pacific and the Kuroshio Current, except for surface carbon, we have very, very low months, 0 to 1 months of skillful forecasts. But as we move into the Eastern Pacific again, especially for temperature, we have very, very high forecast skill with up to 10 months of useful forecasts. in each the Gulf of Alaska and the California Current. And then for carbon and oxygen, we have skillful forecasts up to 10 months, especially in the Gulf of Alaska. An important thing to note here, why is the skill so different in these regions? Well, I've mentioned, of course, some of the dynamical representation, but we also think some of this has to do with representations of INSO in the model. INSO is relatively well represented, and it has a lot of effects and impacts on the Eastern Pacific that it doesn't necessarily have on the Western Pacific. So in conclusion, novel observational products are allowing us to validate subsurface predictions of biogeochemistry for the very first time. CSM SMILE is accurately predicting surface and subsurface marine stressors in a variety of large marine ecosystems. And we have up to 10 months of these useful forecasts in important large marine ecosystems. And with that, I'll open it up to any questions. We're about to submit this paper to Earth's Future and would love any feedback. Thanks.
Thanks, Sam. Any questions? Keith?
Sam, that's nice, great presentation. On your previous slide,
Yes.
in the top right,
Yes.
what do you think's going on with oxygen with those occasional drops and then it goes right back up?
Yeah, so that's a really great question. And you can sort of see a pattern where it almost looks like there's some sort of effective initialization. We have 4 annual initializations I didn't really mention, but we're removing seasonal cycles from all of our analysis. So we're not really sure what's going on here where there's these drop-offs in certain months of the year that are consistent no matter the initialization.
Is it the same month of the year, regardless of which month you're starting with? But like if it's 3 months after November lead, then that would be in February, right?
Yes, it's consistent like that, where
month.
certain months there is a consistent drop-off, which is weird, yeah.
Is there any sort of potential like bias in the observations that are present from those months that maybe they took it at a bad time?
Yeah, there certainly could be. Right, these observational products are the best guess.
Oh, right, these are products.
These products are really the only thing we have for estimating these things, especially in the subsurface ocean. So we're kind of relying on it, and any errors could come from both the model, but also could just come from the observations not necessarily being accurate at these specific times.
Other questions? Okay, thanks.
I have another question actually. Is there any sort of like potential physical mechanisms that might be contributing to like poor model skill in the Kuroshio current system? Like is it like a just like more chaotic system physically that could be, you know, affecting it, or?
From my understanding, it is just the representation of the western boundary current is maybe not the best in CSM, especially compared to the eastern part of the Pacific where we have the upwelling that is pretty well represented in CSM.
Okay, thanks, Sam. So that concludes our set of talks for the meeting today. We have some time now for discussion, but we don't have really a structured format for that discussion. So I would just like to sort of maybe prompt a bit of reflection in the context of what we've seen thus far today on the Ocean BGC, which I think has a few themes, one of which is development around marble. I don't know what caused that. Development around marble and the application or the interest in applying marble increasingly complex configurations to be able to represent coupling with higher trophic levels, as well as improving sort of the fundamental biochemical formulations in that model. Another theme was related to the predictive capacities of the Earth system model on timescales that include, interannual or seasonal to interannual, and as well as the more traditional long-term projection timescales and the impact that climate change has on ocean biochemical distributions and the carbon cycle. That's my characterization, and I just open the floor for topics or comments from people in the context of, the things that we might do as a collective to advance, advance our capacity to address these kinds of research questions. So this is just an opportunity to engage in that conversation as a working group. Go ahead, Nikki.
I would just add to that also, the theme that showed up in every talk was the connection between observations and modeling and how we can make that connection stronger, how we can better compare observations and models, which I think came up a lot in the land model working group, biogeochemistry part this morning, whether it's by having an observational emulator or by other means.
Yeah, that's a great point. I left that one out.
I'm trying to figure out how to get everybody's pictures. Oh, there we go.
Well, there are 11 others that we can't see.
Yeah, I can't get everyone. I can't seem to control that. Maybe Nick can pull the chat up. There we go.
Okay, well, we don't have to have a it's not mandatory, but this is an opportunity to provide feedback or to make suggestions about things that we might do as a collective that we can't necessarily accomplish. Oh, Anne, do you have something to say?
Yes. I would like to hear some status on how Marble is interfacing with the new replacement for moms. Is that in process or is that postponed or what?
It's in process. Should I stop using this mic? So the status of that is that
Can you mute yourself, Ann?
Okay. Okay, the status of Marble implementation in MOM 6 is ongoing. I think we can safely say the majority of the development work is done, but we're sort of in the process of validating the port by comparing Marble solutions in MOM 6 to those to reference solutions in POP. I'll also say that some recent work has focused on enabling a single column version of Marble in a single column MOM 6 test case that we hope will provide a nice tool for parameterization development and educational applications and other things that you might conceive of using a 1D model for. Thanks for that question, Ann. Frank?
I just turn that around and ask this working group, if there are fundamental limitations in the representation of the physical state that have been holding up progress in BGC, that, please engage with those of us in the ocean model working group so that we can work towards a resolution of those problems, especially moving towards the CSM3 release. We're still in a position where we can make some fairly significant changes in our resolutions, configurations, et cetera. And MOM gives us a lot more flexibility in that regard.
Mm-hmm. Yeah, that's a great point. Go ahead.
Yeah, I have a question following up on that. So I know there was sort of, I think if it was with CVIP 6, but with the CESM2 model, there were some like subsurface oxygen issues, like deep oxygen issues. Have those been resolved? What's the status of that?
They have not been resolved.
Okay.
That model still simulates very anemic North Pacific ventilation. And I don't know, Keith, do you want to talk about those? Or it's too painful?
We have had theories about the cause of those issues, but we're not really using that model anymore.
Right.
That's not the model of the future. So we haven't done extensive work on trying out those different theories because we are working on the transition to MOM.
Right, so that was with POP, and so, is the porting into MOM 6 not to the point of seeing those types of things yet, still in the sort of like software coupling phase, or?
Yeah, I don't think we know enough about the circulation of the coupled model with MOM to know if we would be experiencing similar problems.
Okay, just curious.
Well, we do have some longer runs, and we have ideal age, we have CFCs, we have other tracers that hopefully would be indicative of some of the issues we've seen in POP. The problem is we have a very small group of people working on MOM6 development. We need more eyes looking at these other things. So if it's something you're interested in, we welcome your input looking at and help in looking at the whole spectrum of results we have.
Yeah, so I think historically, some of the key biases have been associated with thermocline ventilation and oxygen minimum zone ventilation, and then deep ocean abyssal flows. And yeah, we need to be evaluating these simulations on those metrics.
We have tried to pull these tracers into the model development process at an earlier stage, so we don't get to a release and find out, oh, you can't do BGC with this model. So we're trying to look at it now.
How are the mixed layer depth biases looking in MOM 6?
Gustavo will show that tomorrow.
Okay.
Okay.
Like one word, yeah. Okay.
Okay.
I think we have too deep.
Too deep?
Yeah.
Wow. That's
Keith,
okay.
do you want to go ahead, ask your question?
I was just going to say, for the thermocline ventilation, you don't have to wait for a BGC run. If you could just look at the CFCs in the circulation model.
Yep.
And if we can match those, the oxygen will look good.
Yeah, agreed. Any other thoughts? Okay, well, I proposed.
I would bring back up Nikki's question that we had before lunch, which is from this community, maybe not everyone was sitting in the room before lunch, of thoughts about what would be useful types of emission-driven scenarios, particularly potentially looking at climate mitigation type scenarios. What would this community find interesting in that space? What would we be learning from them? What should those scenarios look like?
Go ahead, Nicola.
2,300 would be nice. That's all. That's gonna be my input
Longer.
now. Yeah, longer. Yeah, just generally sort of like. Yeah, I would like to see emissions-driven ones because I think in a lot of ways, air system models in general, especially CESM, are probably going to get involved with a lot of research being done with sort of nature-based climate solutions and things like that. And I think emissions-based scenarios are really going to be key in those if we're looking at any sort of net zero approaches and things like that. We can't really do much without an emissions-based, so I think that would be great if we could do something like that.
Go ahead, Nikki.
I'll just add that I think having even a small ensemble of simulations would be helpful for characterizing sort of the regional internal variability response to negative emissions in the ocean, probably on land as well. So something to consider, not just one, but an ensemble.
Okay. I propose we adjourn. Thanks everyone for participating in a great meeting, and look forward to the next one.